Well, good morning, everybody. Today is modeling day. We had Monday. We had circulation day. Yesterday was observations day, and today is modeling day. And so Dmitry is going to introduce everybody and be the moderator for this morning session. And this afternoon we have a couple of talks still on modeling, on the modeling theme, and a breakout session that will address a bunch of modeling issues and questions. And the thing that's not on this agenda for today is at 15:30, everybody else gets to go home, but the people that have been moderators and note takers for the breakout sessions, we're asking those folks to sort of stick around, and we'll try and come up with a common story for each of the three breakout periods. And, maybe with a couple of slides that might illustrate what those breakout sessions came up with, and somebody to present it on Thursday. So with that, I think I'll turn it over to Dmitry and Sam and get started. I'm sorry?
Be okay, yeah. I think that should be okay. We have people online. Yeah, it should be good. Your introduction was on time, but the first talk will start early. I think, yeah.
All right. Good morning, everybody. So we're about to start our session 5. And the first presentation is by Liz Douglas from Naval Research Laboratory. And the topic is, what do models and analysis of existing data tell us about models of circulation?
Absolutely. Okay, so my title is actually a little different than what the title they listed for me there. What I'm going to be talking about is Arctic prediction and forecasting to NRL. So just for an outline, I'm going to talk about our former system, which was called GOFS 3.1. Current system is GOFS 3.5. Our future system, ESPC, with some examples of how it's working, and some recent developments and improvements, including an Arctic OSSI project, which we're using to sort of evaluate our entire system and how we use data and how we can better use it. So GOFS stands for Global Ocean Forecasting System. It's a coupled system using a HICOM ocean and SICE sea ice. It's forced by NAVGEM, which is the Navy Global Environmental Model. So that's our atmospheric forcing. And it uses a system called ENCODA, which is the Navy Coupled Ocean Data Assimilation. We assimilate all real-time data that we can get. We've got satellite altimetry, satellite SST, ice concentration, and also in situ profiles. Basically, whatever we can get, we throw it in there. So GOFS 3.1 has been an operational system since November of 2018. It's a global system, 1/12th degree, and they use it for real-time operational forecasting and providing boundary conditions for regional systems. So this is just a picture of what ice thickness looks like. This is ice thickness for July 1st of 2017. It's HICOM plus ice 4, and you can kind of tell from this figure that it's getting a pretty good ice edge, but the thickness doesn't necessarily look like what we might expect what we might expect thickness to look like. So this is what thickness looks like in GOFS 3.5, which is going to be our next operational model. Maybe. Actually, this is a new development. When I wrote this talk, which was 3 weeks ago, that was true. They may have decided not to make GOFS 3.5 operational. We might be skipping it and just going directly to ESPC next. That's kind of up for debate at this point. So it's been used by the Navy, just not as the official operational model, but we are using it for a lot of our modeling at this point. It has size 5 instead of size 4. It includes tides. You can see that the ice thickness looks more realistic. I don't actually have a picture of data, but I'm pretty sure that's what ice looks like. So what's going to be next is ESPC, Earth System Prediction Capability. So GOFS has HICOM and SICE coupled and forced by NavGem, but ESPC fully couples the atmosphere and the ocean and the ice. So all three of those are coupled together. And actually, if you're looking at ESPC version 2, which is what I think is going to be the operational model, it has atmosphere, ocean, sea ice, waves, land surface, and an aerosol model. And they do, a weekly 16-member ensemble for forecasting, and it goes out to 45 days. So that's going to be pretty great once it's fully working. This is kind of an example of sea ice extent prediction from ESPC. So they initialized it in July to predict the minimum sea ice in September. And you can see that the red lines are all the ensemble members. The thicker red line is the prediction, and then the blue line is what it actually was. So it's doing a pretty good job of predicting sea ice extent there. This was another example, the prediction of an ice buoy location during ICEX, which is ice operations up in the Arctic. The red lines are showing the ESB ensemble prediction of the buoy location, and the black line shows where it actually went. So we're doing a pretty good job with ice. So what have we added recently? We have added a simulation of ice thickness, right? The current product uses a simulation of ice concentration, but ice thickness is a new data type that we're adding. So this is at the bottom there on the left showing is before we were initializing thickness, and then on the right, the thickness after reinitializing and running with ice thickness simulation. So it's doing a better job of assimilating this new data type. This is 3 time series of moorings, mooring A, B, and D. The red line shows ESPC, the operational version, the GOFS operational version, and then the blue line is GOFS with ice thickness assimilation. The gray line is the actual data. And so you can see that the RMS improvement is much improved. At mooring A, it's 58%, mooring D is 55%, even mooring B, it's only 5%, but it's still an improvement. So we're doing better with comparisons to data now that we're assimilating these the cryosat ice thickness. Assimilation of VIIRS is another thing that's going to be coming down the line. This is VIIRS data, has a native resolution of 375 meters, so it's super high resolution. And the recent algorithms have been improved. Previously, they were having trouble with distinguishing ice from clouds, but they've improved the algorithm so they can better tell what's ice and what's clouds. And you can see there the VIIRS observations on the left are now showing places where we're adding ice that wouldn't have been there. The ice would have been either misidentified or completely missed, and now it's being added to the model because we have this really high resolution data. We're still working on determining what the quantitative effects on model ice edge and concentration will be. Another development is the parameterization of landfast ice. So, you have the pack ice that's sort of floating and drifting, and then you have landfast ice that's stuck either to the bottom or to the edges. So it's ice that doesn't move. And you can see that in GOFS 3.5 with size 5, we had no landfast ice at all. When you use size 6, the green line shows where the edge of the landfast ice is. And the other thing that you get is you get these leads that open up when the pack ice sort of drifts and the landfast ice is stuck. And the leads are comparing really favorably to, I mean, that's actual imagery from the NIC. And it's looking pretty much just like our model. So we're pretty proud of that how well that parameterization is doing. And size 6 has landfast ice, but we've created kind of more advanced parameterization that's spatially varying in the parameters. Because there's different kinds of landfast ice in different locations. So if you look at the different basins, I mean, on the left you have the Arctic basin overall, but the Beaufort Gyre, Chukchi Sea, East Siberian Sea, and Laptev Sea have each got, you know, their own areas of landfast ice. The green lines are showing what GOFS will get for your landfast ice without the parameterization. The red line is what we get from size 6, and the blue line is NIC data for landfast ice in each of those locations. So we're getting much more realistic results for that. The other thing I want to talk about, so those are the recent improvements that we've put into the NRL modeling system. And the other thing I want to talk about is this Arctic OSSI project. So this is a NOT project collaboration between NRL, FSU, and SIO. And we're trying to basically examine the system and determine the best way to optimize. I mean, are new observations necessary? I think we all know the answer to that is yes. But the question is what new observations are going to do, you know, going to be the most beneficial to us? And also, we're trying to figure out how we can better use the observations that we have. And another question is the system responding in the way that it should to the data? Like, and what assumptions are included in the system that need to be challenged? Like, what are we assuming is true that may not be true as the Arctic has been changing? So I don't know, I guess I just sort of said OSSI like people know what it is, which may or may not be true. OSSI is Observation System Simulation Experiment. So the concept here is you start out by creating 2 nature runs, high resolution, non-assimilating global runs. I'm not going to go into the details of those because Effie Fine will be giving a talk later this morning on the one based on POP, and Dmitry Dukhovskoy is going to be giving one later today on the HICOM one. So they're going to give the details of those actual runs. But from my perspective, those we consider to be nature. Then we sample those as they would be seen by our observing system. We take, you know, SSH tracks that, you know, would be what the satellite sees, or we, you know, take profiles. Basically, we take data from those as we would take from nature, and then we assimilate those into our summative system. And then the nice thing here is we say, this is what our model says, and we can refer back to what the nature runs say. We know what the right answer is, so we can see if we're getting the right answer using our system. A word about that, another important thing is what synthetic profiles are. So ENCODA does not assimilate SSH directly. What it does is it takes an SSH anomaly. SSH is, of course, pretty much the largest data set along with SST, but SSH, we have a ton of it. How are we going to use it if we're not assimilating it directly? We create synthetic profiles of T and S from each SSH anomaly. So basically, we use something called ISOP, which is Improved Synthetic Ocean Profiles. We assume a covariance of SSH anomaly with T and S structure. We say basically, if the SSH is changed by this, it's because either we're this much warmer or we're this much saltier from known covariances based on an SSH or based on a TNS climatology. So the question is, does the current state of the Arctic match the climatology? Or are we kind of forcing our system toward an Arctic that no longer exists? So this is an example. There's 4 figures here. What we're looking at is the temperature at 1,000 meters in the North Atlantic. So you can see Greenland in the top left of these figures. The top left figure is the nature run. That's what, this is the POP nature run. That's what POP says the actual temperature is at that depth. when we do two OSSEs, and one of them we assimilate T and S, the actual profiles from the model, instead of using ISOP. So when we do that, we get pretty close. We get good structures. It pretty much looks like it's supposed to. And then the lower left there, we see climatology. That's what our current climatology, which I believe is GDEM, is saying the temperature and structure should be at that depth. And then in the lower right corner, we have the ISOP OSSE, so the one that's actually using our synthetic profiles of temperature and salinity. And what shows up to me is that those blue temperatures, like basically the climatology and the the ISOP OSSE are getting colder temperatures than they really should be. And this kind of thing is saying, okay, we're getting the temperature wrong at 1,000 meters because we're pushing it towards a climatology, which is not what POP is saying is actually what the temperature is. So this kind of thing, this is just an example. Does this indicate that the climatology of the region has changed? I mean, do we need a new climatology, or is our system going to be basically getting pushed toward what the ocean doesn't look like anymore? Other issues that are being addressed by this ISOP are currently we don't use ISOP in locations that are thought to be unstratified, which is the designation for unstratified is T surface minus T 1,000 is less than 3 degrees Celsius. But we're doing that based on climatology, so we might need to adjust our climatology so that we can use the SSH in different places than where we're using it now. And also, we're curious as to whether we can do better than this. I mean, this choice, like, okay, don't use it if, you know, the top-bottom difference is 3 degrees. I think that was basically made on kind of a mid-latitude assumptions, you know, and I think that if we really focus on the high latitude and say, okay, this is a place where we might have top-bottom differences. Sometimes there's subsurface stratification in some of these locations. We see like major differences, you know, major structure subsurface, but the top-bottom difference isn't large enough for us to use it. We think that there's better ways that we could be using this data instead of just kind of throwing it out. Another thing that we want to look at is the ice edge. Currently, SICE is not assimilating unless the difference between the model and the observations is greater than 10%. Seems like a lot. So there's a question of whether we should try to match this closer, or how else can we improve the ice edge. Ice edges are really difficult to get correct, as it turns out. So that's pretty much it. So it's just summary. We have the Arctic modeling has evolved at NRL from GOS 3.1 to GOS 3.5 to ESBC. We're now including ice thickness, VIIRS, and LFI, and we have these OSSE experiments that are showing us where new changes might need to be made, and what else we should include, and how we can better include things.
Okay, I think we have time for 1 or 2 questions.
Hi, I have a quick question on the level of the uncertainties for the forecast, let's say for the summer ice, in terms of a million square kilometers or something like that. And the second question is that in a table it shows that it can predict up to 45 days. So can it be extended further than 45 days?
I believe they're working on extending the ESBC forecast past 45 days. 45 days is kind of the what they do routinely, but I'm not sure how well it's holding up for longer forecasts than that. The Navy's kind of really interested in short-term things, so that's generally what they focus on.
Right.
Yeah, that was really impressive. This is far advanced from, I think it was PIPS was the polar ice prediction system I remembered. So this seems great. The only thing I caught was that this issue of stratification, and yeah, in high latitudes, temperature difference doesn't mean anything in terms of stratification. There should be some criteria with salinity would probably be
Yeah, again, that's where I think, we're working with a global system here, and when they were setting these criteria, I mean, it's also like 3 degrees from, as far as I can tell from people I've asked, it's pretty arbitrary. So we really need to look more closely and figure out what would be appropriate criteria, salinity in the Arctic, things are just different. I mean, like I've been working with Bob Helber, he's our kind of ISOP person, on trying to figure out how we can do like Arctic ISOP, so we can really use all these, high latitude measurements of SSH. I think it actually just also cuts off at 75. Now I'm not sure how much SSH there is north of 75 north, but there's certainly some that's getting sort of thrown away. And I feel like we need to find a way to use these data that we already have. Like we have data and we're not using them. So we need to figure out how to better exploit those resources that we have.
Do you assimilate any hydrographic data, temperature, salinity data?
Yes, whatever we can get.
And is there a routine place you get that from ITPs or something like that?
We're going out and taking all the data we can find. I mean, it's whatever's publicly available. And then of course the Navy has some special Navy stuff that other people can't have, but
Yeah, okay.
I saw John Toole has his hand up.
Just wanted to say, I think ITP data are going on to
One second.
GTS. Right, and so if you guys get your data from GTS, you should be
One
getting
second, John, sorry.
Just a quick comment on Jamie's remark. The data should be real-time available for operational forecast. So this really limits the amount of data that can be assimilated in GOFs.
yeah, it's
real time.
It's real time, because this is all for an operational system where we need to know they're running it.
John, do you want to try asking your question now?
Wasn't a question, it's just ITP data should be getting out on GTS. And so in basically real time. So if you guys suck in data from GTS, you should be getting ITP data if the system is working.
I can hear John in my headphones. I understand that, but he's not muted. Sorry, John, we're having some AV IT issue. And your question was too complicated for me to repeat. I don't know enough of the acronyms. So maybe we'll save that for the discussion. Our next speaker is virtual, so we do need to figure this out.
Are there any more questions for Liz? Yes, please.
Yeah, it's great to see that the inclusion of the landfast ice parameterization is, it really improves the simulation of sea ice. So did you look at the impact on the ocean regionally, hydrography, and the pan-Arctic circulation? Do you see any impact?
We have not yet, but I want to. It's interesting. Most of the people at NRL are very focused on ice and not so much on the ocean underneath, but I think that there's some really information to be gained from looking at that.
Okay.
Any more questions?
Oh yeah, John, if you want to put your question into the chat, then Liz can read it so that I don't have to parrot it.
Yeah, he says all he was trying to say is that ITP data are supposed to be available via GTS. I believe they are, and they are included, but I'm not positive.
Check. Check, check.
All right. No more questions? Are there any questions online?
No. Can you try talking really quick?
Yes, check, check. Can you hear?
Okay. No, we can't hear. I can hear you on
Yeah,
WebEx,
thank
but I
you,
can't hear you
Liz.
in the room. Maybe we should move the agenda around a little bit. While we figure out this issue. No, not yet. So let's hop ahead.
All right, so we're going to change a little bit the order of the presentations until we fix the technical issue. Our next talk is by Qiang Wang from Alfred Wegener Institute, and the title is Understanding Arctic Ocean Changes with Emerging Modeling Capabilities.
Thank you. Hi, everybody. Yeah, in this presentation, I will share a little bit experience for understanding the Arctic Ocean changes with numeric simulations. So I would like to thank my collaborators listed here for different parts of the work that I will show here. Yeah, a little bit of background. We know already from the presentation during the last 2 days, the buffet gyre has been spun up. Now, what we see here is that a velocity anomaly derived from satellite observation. We can see there's a trend in the surface geothermal current indicating the spin up of the gyre. And at the same time, if you look at the freshwater content in the buffet gyre region in observation and also in our model simulation, we can see the quick increase of freshwater in the buffet gyre at the second half of the 2010s. And then there's a period, meaning the first half of the the first part of 2010s, the fresh content, a small drop in 2014, but largely it's leveled off. And afterwards, in the second half of 2010s, and the freshwater content increased again. And at the same time, as we see, if you look at the variability, the circulation mode in the Arctic Ocean, the center, the location of the active center is different from the center where we see a strong decadal change. And another important change in the Arctic Ocean is the warming of the Atlantic water layer and the uplift of the boundary between the halocline and the Atlantic water layer. And associated with this, the phenomena called Arctic Atlantification in the Eurasian basin, it's basically associated with the uplift of the boundary between the halocline and Atlantic layer, and the weakening of the halocline, which has the potential to facilitate the heat from the Atlantic layer to reach the mixed layer and then to melt sea ice. So with this information, we try to use different kind of model simulations to understand the causes for these changes. So in this talk, I will first to show different experiment from wind perturbation experiment and then the real world simulation. We try to disentangle the main causes for the changes of Arctic Ocean over the last 20 years. Then we look at CMIPS-6 model simulation to assess what will happen to Arctic in the future. And at the end, I will talk a little bit about the current status and prospective ocean modeling in the Arctic, as suggested by Jim, emergent capability of Arctic ocean modeling. So it's some kind of food that which can stimulate the discussion, maybe is up now. Yeah, in this first part, we use our unstructured grid global model called Fizon. It's unstructured, so we can very conveniently use variable resolution. So it's about 1 degree in the global ocean, and then the resolution increased to 24 kilometers in the northern hemisphere, and then in the Arctic Ocean, we use 4.5 kilometer resolution. So we do normal control simulation, and then the second experiment, we add wind perturbation over the Arctic Ocean. The difference of the result between the two simulations tells us the response of the ocean to the applied wind perturbation. So we consider a few cases here. So the first one, up left, shows wind anomaly representing high, Beaufort high. And as we can see that the second row shows the response of the freshwater content to the perturbation. And as we can see that more freshwater is accumulated in the Beaufort dry, no surprise here. And then the second case is positive phase of Arctic oscillation anomaly. Then we can see the release of the freshwater from Mackinac Basin and a little bit increase around in the Beaufort Sea and over the continental shelf. But overall, the total freshwater content is reduced in the Arctic Ocean, which is released to the North Atlantic. And then we combine the two anomalies, and the response, as we can see, is largely a linear combination of the first two experiments. And here we show the upper ocean circulation as shown by arrows, and the color shows the Pacific water indicated by a dye tracer injected in Bering Strait. The very left one is a control simulation. We can see when the Beaufort high, when the anomaly applied, then the Beaufort dry became stronger. And with positive AO forcing, we can see that the transport drift moved toward the Mendeleev ridge, and the size of anticyclonic circulation is reduced. And with the combination of the two faulting anomalies, we can see that both anticyclonic circulation and cyclonic circulation, their strengths are increased. And the location of the transport region certainly is determined by the relative competition between the two faulting anomalies. So this experiment is done in the same climate scenario. Then we move to another experiment, and we will do similar wind perturbation experiment, but with different warming scenario in the Arctic Ocean. In one case, we use atmospheric thermal forcing representing the condition of 2010s, and in another one, we use atmospheric thermal forcing over the Arctic Ocean representing 1980s. Otherwise, all the experiments are the same, and in each condition, thermal condition or CS condition, we do the wind perturbation experiment. And then we compare the response of the ocean to the same wind perturbation. Here we just show one wind forcing is the negative Arctic oscillation case. We see the accumulation of fresh water in the Central Arctic, in the Mackinac Basin, in response to the wind perturbation. And the magnitude, as we can see here clearly, is much larger when CIS is thinner and more mobile in the condition of 2010s. And here we see the difference of seashore height and surface upper ocean current of the ocean response between the two conditions. And then the very right figure shows the current and seashore height response in the warm condition. You can see the magnitude. The difference is about 50% of the absolute response in the warm condition. That means it's almost the same as the response, the magnitude of response in the cold condition. It's a really considerable increase of the response to the same wind perturbation. And we can also look at the total freshwater content response to the wind perturbation in the two conditions. The red is for the warm condition, the blue is for the cold condition. We can see that after 10 years, that's about 50% higher for the warm condition in terms of the response, the increase of the fresh content in the whole Arctic Ocean. It's less pronounced than the local response because, as we can see in the upper left figures, when there's increase around this increase, there's some drop. So the total increase is less pronounced. But it's also interesting to see that when we apply another vent perturbation, the positive AO, so then the ocean will release fresh water. We can see that also in the warm conditions, the release will be stronger. That means the availability of the Arctic Ocean will be stronger with reduced CS coverage. With the understanding in this simple experiment, now we move to the real world. First, we look at the sea level pressure for different periods. The first one is the second half of the 2000s, and the middle one is the first half of the 2010s, and then the upper right figure shows the period for the second half of the 2010s, the most recent period. The sea level pressure anomaly referring to the long-term mean. So in the first period, we see a strong Beaufort high, as shown in the time series below, and addressed by the green background color. The first one, we have a strong negative convergence phase of fresh water. And if you look at the very recent period and the upper right figure, the sea level pressure is close to be neutral, a little bit negative than the long-term mean. But if you look at the curve of the vent, the second green background region is again strongly negative. That means, although the sea level pressure is lower in the Beaufort region than normal, but there's a strong negative anomaly in the vent curve because the sea level pressure around continental basin is even lower. So, and if you look at the red time series, the red line in the bottom figure, it represents the 5-year rounding mean AO index in the very recent period is in a positive phase on average, although it's less pronounced compared to the end of 1980s, beginning of 1990s, but on average it's in the positive phase. As shown in the sea level pressure normally in the upper right figure, you can see the blue negative value. And to disentangle the impact of the wind and sea ice change on the Arctic Ocean, so we need extra experiment. First, we have the historic simulation representing the past. We try to force the model with reanalysis to get the historic period for the ocean and sea ice, and then we do another simulation of the same, just we replace the atmospheric thermal forcing over the Arctic domain by the climatology. But the wind is kept the same. And then what we see here is the difference of ocean surface freshwater flux. Largely it's because of the melting of sea ice in the historical simulation. Because in the second experiment, the thermal forcing remains the same. There's no sea ice decline. There's only internal variability there. So the difference of surface freshwater flux is just because of the sea ice decline in the first experiment. And what we see here in the bottom is the difference of sea ice drift between the two simulations. We can see with sea ice decline in the real world, the sea ice speed is increased, representing the pattern represents the climatology of sea ice drift, stronger both just circulation in sea ice and also stronger transpolar drift in sea ice. But if we look at the ocean surface stress in the middle, bottom middle figure, the arrow shows the direction of the difference of ocean surface stress, and we can see that it has very different pattern, the direction, compared to the change in sea ice. That's because when the ocean sees the change of sea ice, the ocean surface current changed, and then the ocean surface stress is not just a function of a change in sea ice drift. And anyway, we can see the red color, that means the ocean surface stress largely over the aftermath is increased, and the right figure shows the direction of the surface Ekman transport. You can see that largely is directed from the Morison basin toward the macro basin. So later we will look at the impact of sea decline on the ocean. Just remember is the effect of increased surface freshwater flux in the historic simulation, and then also through the changes in the ocean surface stress reflected in the surface Ekman transport. Again, we look at the 3 periods. Now we see the change of the freshwater content through the 3 periods. So there's no surprise in the first period from 2005 to 2009, there's strong increase in freshwater content in the Baltic region in response to the high sea level pressure. And in the second period, both AO and the wind curve over the above the dry is relatively in the neutral state, although not exactly. So it's the phase of leveling off of the fresh content in the above dry region, although we see a small drop as reflected in I mentioned 2014. And then in the very recent period, the freshwater content continued to increase in response to the strong negative wind curve. Look at the center a little bit different from the first period because it's more to the southwest of the Kandan basin. And at the same time, we see the drop of freshwater content in the macro basin and partially in the Wilson basin in response to the positive AO phase. This is a result from the historical simulation. Now what you see is the result from the experiment with Arctic thermoforcing representing the climatology. Otherwise, remember the experiment is the same as the first one, especially the wind forcing is the same in the simulation. And if you look at the pattern, more or less, they are the same. But if you look at the magnitude of the change in the freshwater content, for example, in the first phase, we also see the increase of freshwater content in the Baltic region, but the magnitude is much smaller. And also, especially in the second phase, in the historic simulation, the freshwater content basically is leveled off. But without CR decline, we can see a strong drop of freshwater content in the Baltic region. That means in the real world, the freshwater content stopped to increase, but didn't really drop a lot. It's because of CR decline. Otherwise, as we can expect, in the first phase, we have a strong convergent freshwater, and in the second phase, when it's a neutral phase, then we expect the reduction of freshwater content. Then we did a UF analysis of seasonal height. The first mode and second mode is shown here. This is for the historic simulation, but if we do the same for the second experiment, we can see we're quite different pattern and magnitude. That means we try to do UF to understand the mode of the ocean circulation and try to link it with the wind, but we should not forget the mediation effect of sea ice cannot be forgotten. And then we can look at the phenomenal identification. Shown here in the first column is upper ocean salinity. We can see the strong difference between the 2 experiments, and then the second column is the depth of the halocline lower boundary. We can see that in the historic simulation, the first one, we got a shallower trend in the depth, but without CR decline, then actually the depth did not change much. Then we can look at the temperature in the Atlantic water layer. Also, because of CR decline, the warming trend is much stronger. That means the Atlantification in the Eurasian basin is driven by CR decline, not vice versa. And then we can look at what will happen in the future. Again, I want to address the effect of the dynamic effect of CR decline. So we did a different experiment, tried to use different thermal forcing derived from a couple model. We run the ocean model again. We look at the surface Ekman transport, The first figure up left is the absolute value. The other are the anomaly in different warming conditions referring to the first one. We can see that the magnitude shown by the green color is increased with CR decline, but the direction remains largely from the Earth basin toward the Maclo basin and to the Canada basin. And then in response, here we show the salinity crossing the Arctic basin. The effect of CR decline is to continue to increase salinity in the Earthen basin and reduce salinity in the Canada basin. And in all the experiments, the surface freshwater flux is kept the same. So the impact is meaning the dynamic effect of CR decline. So when we understand the model results, usually we can get different freshwater flux, we have closed budget, but the dynamic effect is not directly the model output. So only through such kind of sensitivity experiment we can really to get the feeling how important of the dynamic effect in expanding the change of the Arctic Ocean. And then quickly we can look at, I will just quickly show the result from our analysis of CMIP6 result. The left figure shows the zone mean temperature difference at the end of the century compared to the end of the last century. We can see the strong warming in the Arctic region and stronger than the global mean, and also shown by the 2D plot. Although not necessarily higher than every point, but if basin-wise, the Arctic basin has the strongest warming. So we identify this and we call this Arctic Ocean amplification. And actually, if we compute the amplification factor for different depth ranges, we see that the strongest amplification is in the Atlantic water layer. This can be explained by the increasing convergence of ocean heat through Arctic gateways, as shown by the red line. And the blue line shows the ocean surface heat loss. That means the Atlantification, more heat converged from the Atlantic into the Arctic Ocean. It's caused the Arctic Ocean amplification. At the same time, it contributes to the Arctic atmospheric amplification. And then we will see this is not something for the future, but actually it has already emerged. Because if you look at the amplification factor from the CMIP6 models, after the strong oscillations, then it stabilized at the end of the last century already. And then we look at CSM, large ensemble, 40 ensemble members. We show the distribution when Arctic Ocean amplification has happened. We can see that it's centered at about 1980s, but actually before 2020, all the 40 members has already shown Arctic Ocean amplification. And I think I don't have time, so I will neglect this last part, and we can communicate a bit. I want to show that that's large model bias. Although the CMIP6 model, for example, is the best we can have to understand the Arctic future changes, but we have a large model bias. We have to keep this in mind when we interpret the model result. But we see here by increasing resolution, we can really reduce the model bias, especially the deepening of the Atlantic layer, for example, by increasing model resolution. And the increased model resolution to 1 kilometer, we can better resolve the eddy activity. Basically, it provides a tool for understanding Arctic small scale, and it's linked with the large scale phenomena. For example, here the very last part, just an example that not only for understanding the dynamics, but also we can learn how important are the eddies in the Arctic Ocean. Here we just zoom to the firm street. You can see the eddies. What's the rule of eddies as shown by the bottom figure? Without symmetric eddy with a medium resolution, as shown at the bottom left figure, there's big temperature bias in the simulated field. When the eddy are resolved, which actually has the effect to bring the warm water across isobars, and then it changes the recirculation and the location where the Atlantic water recirculates and the strength of the current in different locations. We can see that then the model can better represent the observed temperature as shown the dot in the background. So with this, I finish. I don't want to repeat because I'll use too much time. And thank you for your attention.
Well, we have to move on in the interest of time. So is Anne online? Sam,
Yes, Anne's online.
okay?
You want to try sharing your screen?
Yeah, can you also test the audio? Does it work?
Yeah,
It
we can.
is working.
Yeah, we can
Last
hear you,
night.
Anne. Hello,
Yeah,
Anne.
that's great. All
Yeah.
right, let me try to share my screen.
So our next presentation is by Nguyen from University of Texas at Austin, and the title is Synthesis of Historical Observations Through Reanalysis.
Yeah, you can put, if you put it in presenter mode.
Yeah.
like
Do
you're
you
good
see
to go.
the presenter mode now?
Yep.
Yeah. All right. Thank you very much for I changed the title a little bit by adding the blue here, synthesis of not just historical but modern observations through reanalysis. And I will discuss a little bit on the successes and a lot of the time actually on the challenges as we are trying to understand and making the connection with observations in this workshop. So first I put the vision of the workshops organizers here so that I can try to phrase my talk within the context. So the big picture goal is for us to understand and assess our understanding of the circulation and changes and discuss the observing system requirements to track those changes. So it is in that context that I want to frame my talk, to talk about the feedbacks between the model simulation, data assimilation system versus the observational analysis and how the two feed together, and hopefully to try to improve both. And I make a step back a little bit to try to explain maybe the terminology of data assimilation, because it seems to me there potentially can still be some kind of confusion when we say we use a reanalysis product that one is aware what one is using. So I explained a little bit, and a lot of the time it actually depends on the scientific goals we want to achieve, and therefore the kind of methodology or the kind of reanalysis product we are looking for. So again, I put in gray here the workshops, the big picture, but as we have heard this morning, for example, the different system focusing on forecasting, prediction, and therefore the short-term goal and the kind of requirements are different than if we are aiming for a system that is for budget closure, for where the model physics consistency is imposed, where it is a requirement, etc. And that's also a different system than if you want to use the reanalysis for uncertainty estimate, for example. And so that's the difference in the goals and the methodology can be summarized somewhat in this cartoon of the difference between the trajectories of reanalysis in black versus in light blue in the presence of the data, which are depicting here in the gray triangle. So one of the things we can see, for example, depending on the method. So in one case, if you are to use generally the sequential filter method of data assimilation, then typically you have a model trajectory following its physics in the black. And then when you have the observation arriving at, for example, in this case, as a function of time, then due to the requirement of the reanalysis, then the system is will be brought into agreement with the observation, depending on whatever the criteria, but it can often be the case that there would be a jump in the actual state of the model, the hydrography or the sea ice, because the requirement is quite strict for it to obey the observations. And so that's actually different than another approach. So these are the what's called the filter with short assimilation windows for different purpose. And for a different type of data assimilation, what's called the smoother method for DVAR, but with the key is with very long assimilation windows. For example, in a case where the assimilation window is the entire time period of the model run, in which case the model trajectory simply follows its physics, and it is brought into general agreement with the data, but it does not fit precisely where the data are, because it is also being constrained to follow the physics. And so I want you to keep that in mind when we begin to talk about data assimilation, how to use it, and how we can improve the data assimilation based on the data distribution. So I list some examples here of high latitude regional ocean sea ice reanalysis. It's not a very comprehensive list, obviously, because, for example, it's not listed the Navy's effort that was discussed earlier this morning. One product is the Arctic Subpolar Gyre State Estimate, the release one. This is something we produced last year. I will elaborate a little bit more on. There's the regional Arctic reanalysis produced at Maryland by Jim Carton, in progress, I think, for the publication. Topaz from NERSC, and Biomass from UW, for example. And then there are other efforts that are more global that include also the high latitudes. And in addition to the ocean sea ice, there's also atmospheric reanalysis, often being part of a coupled system, or in some cases they are the what's typically be used to force the ice-ocean system. And some efforts are, or most efforts are global, and some now begin to have more focused regions. For example, this is a high resolution focusing on the Nordic seas, called CARA, that are produced by ECMWF, and then MERA, JRF 55, etc. And I want to use just one example, in this case, the ASTER release one, as an example to highlight some of the persistent biases that we are still seeing in general in data assimilation, and highlight some of the reasons why. So first, just brief word on ASTER release one. Is one of the first of its kind for Arctic subpolar North Atlantic ocean sea ice reanalysis that the main focus is for climate studies, and therefore it's multi-decadal, and it is fit to a very diverse set of low latitude in the North Atlantic, as well as high latitudes, including a lot of the data that had been mentioned, for example, ITP, all the gateways, transports, and mooring arrays. And the model dynamics are what is used as the interpolator for where there's no data. So this is the one where we are using the 4D VAR smoother non-sequential assimilation technique with the strict obedience to the model physics to ensure the dynamical consistency for the purpose of closing budgets. And we are achieving the misfit reduction by accounting for or by adjusting for uncertain input parameters, which I will elaborate in the next 3 slides. And the uncertain input parameters include what we are not solving for in the solution. So that's surface forcing, internal mixing, initial conditions. And in terms of the observational constraint, I give here an example because the solution, the assessment of it is very, wide and diverse and detailed. So if we take an example of the subsurface hydrography, then ITP was extremely crucial in constraining the subsurface hydrography in the Arctic, in particular, obviously, where the data are distributed, which is in the Canada Basin interior. And the Fram Strait is another very important tie point for volume and heat fluxes into the Arctic. But I want to highlight also, this is something that has already been discussed in this workshop, obviously, that the observational density distribution is focusing more downstream of the Atlantic water inflow. For example, so for a case of trying to constrain the Atlantic water inflow, as an example here, and I drew this this blue line sort of depicting the consensus understanding of the Atlantic water inflow. And one of the key things we see is that due to the lack of the observation upstream. So there, what it maps into is there are many non-unique ways for us to try to improve the parameters upstream here before the water finally arrive downstream in the interior of the Canada Basin. And due to that, in the upstream regions in the Eastern Arctic, there are still very strong persistent reanalysis error or biases. And I will elaborate in the next two slides a little more about the non-uniqueness problem pertaining to lack of pertaining to the data distribution problem in the high latitudes. So before that, I step back just a little bit because this is an example for the Atlantic water circulation. This is just an example, but it sort of tie in a little bit with John's discussion on Monday on the topic for in this case, for example, the Atlantic water circulation. And because John had talked extensively about the history of how the circulation was reduced, so here I simply sort of paraphrasing what John mentioned, and primarily that they were obtained historically and even up to present from hydrography data. And a lot of the time, so these are the various deduction based on typically you have sections of hydrography, and because we know the temperature is high upstream in the Atlantic water column, low in downstream of it, and from physics, etc., that it was deducing that that's the type of circulation that we anticipate, therefore the consensus understanding of the Arctic circulation. And on top of it, there are also a lot of theory to help the understanding of why we think the circulation is one way, for example, in the high latitude. And that's summarized in Marie-Louise' paper in 2020. And a lot of these, as you can see, based on the previous presentation, we rely on the model and the physics sometimes to help us understand the mechanisms. But often to try to understand the mechanism, sometimes it helps to also reduce the space, simplify the geometry a little bit to really see the feedback between the forcing and something, the response of the system. However, if we were to apply it to now realistic bathymetry, for example, realistic forcing in the Arctic, so I show here a sort of flavor of model run where I start from the same initial condition using the same forcing, and because I have uncertain parameters related to the dissipation of the related to, for example, side drag or bottom drag, how that is parameterized and how that is quantified, horizontal eddy stirring induced diffusion, dipycno mixing, and ice ocean drag. So these are the various things I adjust, for example, just as a demonstration that you have quite a variety of things that can happen upstream prior to the water eventually will end up interior of the Canada Basin. And as you can see, our hope is that any improved observation can help to constrain some of these uncertainty upstream here, because otherwise there are many ways we can fiddle around with trying to see what might fit the consensus or something, but that would defeat the purpose of trying to actually get something dynamically consistent if we have observation to help us constrain that. And some of these, the circulation also reverse, for example, in some so you can actually achieve some variety of circulation and how the water can get down to the Canada Basin to finally fit with the ATP data. So that's what we mean when we say there are non-unique solutions for the inversion problem to get the parameters. So we would hope to have the observation to help constrain that. And the consequence of having unconstrained parameters, this is actually a well-known problem, that the model will drift. And that's what was discussed also in the previous talk. And this is true for all models due to its numerical limitations, the representation, we don't capture all of the physics. And I quote here from the lessons learned in the lower latitudes and more so in the high latitudes. But in the lower latitudes, it has been shown that for subsurface hydrography, when Argo data were not tightly constrained to a data assimilation system, then the model trajectories can diverge very quickly in periods of months, or in energetic regions, it can actually diverge within days. And so in that case, how would a data assimilation system address these kind of model drifts? So in a sequential approach, you can fix this kind of model drift by reinitialization using shorter assimilation windows. And that is why typically you can achieve a good fit to where you have data, because the problem simply can help reinitialize at the time of the beginning of the assimilation system. And if non-sequential data assimilations are used, then in this case, the misfit would then be mapped into these unconstrained and non-unique ways to adjust for the parameters. And that's why, for example, it is not a guarantee that it would fit the solution, the data at the observation point, but it does follow the model physics. So often when we try to compare products for where we have observation, we need to be careful, because these comparisons are not really telling us a story, a consistent story, and therefore to say one fits better than other, that's actually a language that should be carefully considered. So in addition to these internal parameters that I talked about, there's also, for example, reanalysis, that a system for sea ice and ocean reanalysis in the Arctic we use. And that's we use the atmospheric reanalysis as the input as well in our case. And the high latitude is actually again, a place even for the atmosphere with severe lacking of data, and therefore it has the largest spread of estimates. For example, this is the case for air temperature at 2 meters, and there's a spread of up to 6 degrees Celsius between the different products, with some of the most often used products being, for example, on the high end of the bias. And there also had been studies for reanalysis in the atmosphere in the Arctic to try to understand why, in order to improve. But in the end, the conclusion is often the same, that is due to the paucity of or the lack of observations. Often what you get in a reanalysis in this case then is sort of a unconstrained model run, and therefore what you see normally in the spread is actually just the general model spread. And for that case, then it should be, we should be a little careful when we then try to use reanalysis for studying trends or changes, because it has been known quite well, at least in the atmospheric community, that sometimes the trend is literally due to the analysis increments, due to these adjustments. So this is an example here for Topaz. This is now ocean, the Topaz system, where this graph sort of show where there's no observation, and then when there is observation. And so again, as I mentioned to you, because it is of short assimilation window, so therefore it can actually it can fit the observation when there is. But just by looking at this here, we can already see that potentially, spatially, you can introduce jumps, and temporally, you are now introducing potential trends that are actually artificial due to the distribution of the observations. So we do need to be careful of this when we use the reanalysis, because actually there had been publications of trying to evaluate a product where there is observations, and then following that kind of reasoning, it is then now being used to study changes. And so that's why I thought it was important to actually highlight a little bit the importance of understanding the reanalysis. And so now I tie back to the goal of what we are trying to achieve. I think we can always try to use the assimilation system to, depending on the goal again, but hopefully we try to also understand and improve the model physics. And if that's the case, then we can try to understand observation system design in the sense of trying to improve the constraint for parameters that have large impact in the model trajectory, but however, very under constraint. And it's important then to identify the goals on what we want to focus on, and therefore trying to see what kind of observation we want to use. And I tied them all together to say that similar to what was also presented earlier, one of the key things we can do is to assess critically the past, the present, and future observation system. And some of that work actually had already been, examples were from Nora Loser, worked in the last 2 years to try to assess the complementarity, the redundancy, or the potential proxy for new observation, as well as some of our work on doing OSCE to try to understand potential of new observations to constrain the parameters. Yeah, sorry, I know I run out of time. Thank you very much. And I can take questions if there's time otherwise. Yeah.
Thank you. Anne, are there any questions for Anne?
I think we have time for one, yeah.
I think there was a question from someone online.
Oh yeah, Ben, you put something in the chat. Do you want to unmute and ask?
Actually, I just had a little separate conversation with John about this. So yeah, I think they are using apparently updated reference fields of historical data. So I suppose some long-term variability you would still see in that data. It's just to keep that in mind. And maybe it's not important for the sort of adjustment you do with your assimilation method, since you're smoothing anyway. You probably wouldn't lose it. Just a question to. I suppose you're just treating it the same as any other part of the profile that you assimilate, right?
Are you asking me or John?
Sorry, yeah. Sorry, I probably you didn't read what I wrote. Sorry
No, I can't see that screen.
No. I was pointing out that the deeper parts of the profiles in the ITPs are actually adjusted. The conductivity is adjusted to correct for sensor drift, and that's using historical data. And then I was pointing out that maybe you wouldn't see the long-term variability in your model if you use that to simulate. But then John pointed out that they do update their reference fields. So I suppose that's that's a factor that you would still see the longer term stuff, and given the depth, you probably wouldn't expect too much short-term strong variability.
And I have a question.
Yeah.
Dmitry, so I understand that you assimilate temperature salinity profiles, correct? What other variables do you assimilate?
So let's see, the hydrography, the sea surface salinity, sea surface temperature, sea surface height, the mooring arrays at the gate. So for example, the Fram's rate ended up being very important. We actually use also the GRACE data for the ocean bottom pressure. And I actually have a figure for all of the data that we use, but pretty much the satellite, sea ice concentration, and the sea ice concentration was used as an active variable for the release one, while the thickness would use as a passive only for assessment, because during release one, we had not yet working out the detail for the sea ice adjoint. But now that we have shown the sea ice adjoint is fully working, that's the next step will be to have the active sea ice thickness cost as well. And same with sea ice drift now to help constrain, for example, the drags between ice ocean.
All right, thank you. Sam, do we want to move on? Or?
Yes, we should move on to the next talk.
Thank you, Anne. We have another question. Do you want to ask? Okay. All right. Yeah, let's keep it for the discussion. Yeah, thank you, Anne. And we're moving on to our next speaker, Kat Smith from Los Alamos National Laboratory. And she is going to talk about physical mechanisms of upper ocean mixing in the Arctic.
Hi, my name is Kat, and I work at Alamos National Lab, and I'm going to talk about some of the work that I have been doing, ongoing work that I've been doing as part of the Interdisciplinary Research for Arctic Coastal or Interface Project, Arctic Coastal Environments Project, which is a collaboration between several DOE national labs and the University of Alaska. So as many of you know, sea ice has historically buffered the surface of the Arctic Ocean, and it basically forcing mechanisms that might be more energetic. It basically buffers it from forcing mechanisms that might be more energetic, like wind. And this layer is important for many different physical and biological and chemical reasons. Not going to list them because I'm sure many of you already know this. And it's got far-reaching effects, right? So if we want to have accurate predictions of the Arctic and the climate in general, we need to have a better assessment of our upper ocean Arctic stratification. But Arctic sea ice is in decline and ice-free periods are decreasing. So that means as Arctic sea ice cover goes down, our exposure to atmospheric forcing or higher energy sources of forcing are going to go up. So this kind of brings up a couple of questions. What are the dominant mechanisms of vertical heat transport and mixing in the Arctic, and how are these going to change in the future as we have less sea ice? The figure on the left is from Rainbow et al. 2011, and it kind of shows some of the different mechanisms of mixing that might happen between ice cover and less ice cover. And I think what maybe the more important question here is, are these mechanisms captured by vertical mixing parameterizations? Most vertical mix and most parameterizations in general in our system models are validated with mid-latitude data, which are generally alpha oceans, who are temperature dominated. They're not salinity dominated. They're not ice covered, et cetera. I can go on. So it's not clear that these are tuned the best for the Arctic or even appropriate for the Arctic. And I'll say we're just now getting into that second question, right? So we're working on that, and I just have some preliminary back of the envelope kind of results. Okay, so observations. I'm really using none of my titles to my slides are showing up. Anyways, so some observations, and we've got lots of observations out there to help us constrain our parameterizations, but we don't necessarily have universal coverage of the entire Arctic. We don't have all of the different higher order terms that we might want in order to tune them or validate them. So then we can move to simulations. We have a bunch of different simulations that are ice covered, but almost none that address the Arctic that are not ice covered. And additionally, many of these don't necessarily include salt. And so that's quite important for the Arctic. So I'm going to do large eddy simulations that are basically going to have very idealized constant forcing for 5 days. You can argue that that's not necessarily super realistic, but that's what we're starting with, right? And I'm not going to go into the details, sorry. So our initial conditions come from the ice tethered profilers, where we took some ITP drift tracks and came up with initial conditions. And one thing you'll note from here, which I'm sure many of you are already aware of, the density profile is largely set by the salinity, right? And then our forcing comes from NCEP reanalysis, where we basically took the exact same location. So the Beaufort Gyre is where we're focusing, mostly because this is a DOE project, and so we focus on American coastlines. And so we took NCEP reanalysis from the same place and took relative maximums and minimums and a range within there, and came up with this forcing space here, where we have surface cooling simulations, wind simulations, evaporation, and then 2 different types of sea ice, where there's a drifting one and a land-fast one. And here, I'll note that, like many of the other LES simulations with ice, we're parameterizing the ice melt with a parameterization. And so next step to this whole project is to actually do an explicit ice model coupled to the LES. And so that will be a fun next step. So we did 22 simulations and just kind of break down this table a little bit for you guys. We've got cooling simulations, evaporation, and then wind simulations. I'm going to color those in this way, and then I'm also going to put them into, those are my single forcing cases. And then we've got evaporation and cooling cases, cooling and wind cases, and then evaporating, cooling and wind cases. And those colored this way and separated into multi-forcing cases. And then we've got LFI, which is land fast ice, and then SID, which is surface ice drift. And those I'm going to label as my ice covered cases. To kind of orient you and get you started, here's temperature and salinity after the 5 days of the simulation. And the first thing that you're going to notice is that without wind to act as a buffer, the wind, or without ice to act as a buffer, the wind erodes away the stratification pretty quickly. So these profiles here that are deep in the temperature and salinity profiles, so temperature's at top, salinity's at bottom. And let me just, the first row is the surface forcing cases, or single forcing cases, so that's the cooling, wind, and evaporation. The middle row is the multi-forcings, and then the last row, or the last column, sorry, my apologies. First column, second column, third column is just the ice ones. And so anything with wind deepens the mixed layer and erodes into the mixed layer really quickly. And then additionally, salinity is not, salinity is what dictates the maintenance and erosion of the stratification profile. So unlike mid-latitudes, which is where we validate our parameterizations, cooling or temperature-driven convection is not really something that causes much turbulence or erosion of the mixed layer here. And I mean, I'm probably not saying anything that's all that surprising to many of you, but this is, something we need to go through. So you see here that there's more than a temperature of like 1.5 degrees change in the temperature here, but we see no difference and no erosion into the mixed layer, or the mixed layer depth. And then additionally, I kind of alluded to this yesterday with our evaporative cases, we actually get this little step that's happening here. And I kind of wonder, although I haven't dug into it, whether or not this is the salinity kind of sitting on the base of the mixed layer depth and just starting to strengthen it a little bit more. Unfortunately, I didn't inject a tracer along with it, a passive tracer along with this. This would have been really awesome and it would have told us a little bit more, but we didn't do that. Okay. Now we're going to look at change in mixed layer heat content. And first you'll notice that for all of the ice cases again, we've broken it up into single forcing, multi-forcing, and then ice cases. And the ice cases are 2 orders of magnitude lower in their heat content change, not surprising. And then we can see also that as the wind erodes the salinity stratification buffer, it drives heat into the mixed layer, far more than many of the other methods or mechanisms. And presumably, though we don't model this would cause more sea ice loss and less sea ice growth in the future. Additionally, I want to point out when we look at the multi-forcing cases, things get a little bit more complicated. Initially, we see that cooling starts to dominate, but then after the wind is able to get down to the base of the mixed layer, it really starts to dominate and shoots up and really starts to heat up the mixed layer. Yeah. Okay, and then we can also look at heat and salt fluxes for the averaged over the last 12 hours. And you can see here, same as before, the ice covered cases are relatively negligible, or at least they're orders of magnitude smaller than without the ice. And so, yep. And then the largest fluxes in both heat and salt happen in the wind cases and to some extent the evaporation cases. Okay, so to address these 2 questions, we're first going to start with dominant mechanisms of vertical heat transport in the Arctic. And we're going to look at the vertical heat flux budget. So we've got various different terms here: the gradient production, the buoyancy production, transport and pressure work, and then dissipation. I'm additionally going to break up the buoyancy production term into a salinity and temperature term. I'm just going to plot the salinity term. What you can see here, so right now I'm only plotting the strongest of each of the cases. So in each of the panels here is the strongest for each of that forcing type. Right? And what you can see here is It's a little bit hard to see, but basically this is a blue line. Oh, you can't see a pointer on here. The bummer. Purple starred line on top of it. So what you can see here is that largely it's the buoyancy term that drives the heat flux. And then furthermore, it's the salt contribution to that buoyancy flux that's really driving it, right? So that's the major conclusions from this. Then we can move on to dominant mixing mechanisms in the Arctic. And for that, we're going to look at the TKE budget over the last 12 hours. And similarly, we can break it up into various different terms. And again, I'm only showing the strongest cases here, just because it would be a lot to show all 22 cases. And here, and we'll also split out the buoyancy term. And here we're seeing that mixing is driven by a combo of shear and buoyancy. It largely looks like it's buoyancy here, but there is some shear in the wind cases. There's some shear that's happening at the surface. And so I think a better way to look at this is in time. So this is the shear and buoyancy terms that have been integrated over the mixed layer depth and then plotted through time. Right, so the shear term, what you can see here is that it dominates initially with the wind. This is just a wind case, but this is true for all of the cases that have wind in it. So the wind initially dominates and kicks off turbulence, and then when it hits the bottom of the mixed layer, then it starts bringing up that warmer, salty water, and the buoyancy takes over, right? As you can see, the purple stars are right on top of the buoyancy line, and that's basically saying, again, the salt contribution to the buoyancy term is what dominates here. Okay, are these mechanisms captured by parameterization? Again, most of the validation has been done for mid-latitudes. So this is a really quick and dirty test that I did, and this is not a full. Don't take too many conclusions from this, but this is the start of the direction where we're going with this, right? So I used MPASO, which is the ocean version or the ocean component of E3SM's, which is the DOE's climate model, using the CVMix package, which has both KPP and Pakanowski and Flanders as their vertical mixing models. And I used default values in MPASO and default values in CVMix. No tuning was done here or anything like that for the Arctic or for anything else. And I'm doing a column model only. And additionally, we're not doing ice here yet. So that's kind of a next step as well. So if I'm looking at just a cooling case, the top row is mid-latitude type, initial conditions. The bottom row is Arctic initial conditions, the same ones that we use for these simulations. The black line is LES results. And then red is KPP and blue is Pakanowski and Flander. You can't really differentiate between all of those because they're actually doing a pretty good job here. Second one, wind. So this is a modest wind forcing, and same things are plotted here. Top row is mid-latitude salt and temperature. Bottom row is Arctic temperature and salinity. And as you can see here, with just the default values, again, that's a caveat, we're not doing so well. So I'll give that a thumbs down for now, at least. So I think, it's very possible that tuning would help a lot here, but this is the direction we're going. Okay, so what are the, going back to those questions, what are the dominant mixing mechanisms and heat transport mechanisms? Wind and evaporation to some extent have the largest effects on mixed layer depth, turbulent kinetic energy, heat entrainment, and heat flux. Salinity dictates the buoyancy flux and the stability of the picnic line and not temperature, unlike the mid-latitudes. Again, I'm probably not saying anything that anyone's not already aware of here. And then I think also it's important that in those multi-forcing cases that we possibly have this, it's possible that although even we may have winter cooling, the wind is just going to blast through that, and and successively we're going to have less. We're going to be less able to cool over the winter, and wind is going to take over. In terms of the parameterization, convecting forcing looks good with out-of-the-box parameters, but shear not so much. This is supposed to say future steps at the top of this. So future steps for each of these questions. I'd like to add more forcing scenarios, river, coastal, time varying forcing would be great. And then, as I mentioned before, an actual explicit sea ice model coupled to this, so we can look at deformation effects and thermodynamic feedbacks. We don't really have any of that, and I don't think anyone has really done that with large eddy like high resolution simulations. It may turn out that it's not that important, but we need to check that, right? Yeah, there's that one. I'd also like to next time include a passive tracer along with the salinity and temperature so that we can see where that water is going. For the parameterization, does tuning remedy some of the issues that I was seeing here? And if so, do they have to be different in the Arctic and the mid-latitudes? Probably, I would guess. And then what mechanisms are missing if we can't just tune out those differences, right? And then also to test more parameterizations, one of which is a new assumed distribution closure that we're developing at LANL that is a higher order mass flux model that would hopefully remedy some of these situations. And then also to compare some fluxes and higher order statistics. This is kind of one of the advantages of using high resolution models is that we can get all of those higher order statistics, right? So. And I think something I don't note here is to also use observations and kind of, help along with some of this stuff. I haven't really, other than the initial conditions of forcings, I haven't really used observations here. So, thank you.
All right, thank you, Kat. Are there any questions?
Thanks, Kat. That was really great. This is Marian Alberti. So my question is, so for these cases, you're assuming a horizontal uniform setup, is that right?
Yes.
Okay, and so for one thing that kind of pops out, if you look at any of the satellite observations of the Arctic, is this, and because of the kind of spatial distribution of melting sea ice in the summer, these strong lateral gradients. And I'm wondering if you have any sense about whether those lateral gradients and the restratification that can come out as a result, do you have a sense or any plan to look at how those can compete with the effects of the wind to erode the mix layer?
Are you talking about inhomogeneity in ice cover or in the other forcings that I did?
Inhomogeneity and ice cover and how that leads to inhomogeneity and the buoyancy at the surface.
Yeah, so there are people that have looked at that in similar ways. So there's at least a couple of different studies that have looked at sea ice leads and also just inhomogeneous forcing for that. And it does have an effect for sure. We didn't touch that because some people have already done that. I think that we'll probably touch on that when we go to the actual ice model coupled. And then I think that's where our contribution to that will be. Yeah.
Hi, this is Mike Steele. Is Cecilia Peralta-Fariz here or online? Maybe not. So Cecilia and Rebecca Woodgate wrote a great paper about mixed layer change, historical change in the Arctic. And I think they came to the same conclusion, if I understood what you said, right, that wind mixing is more important than buoyancy. Wind forcing is more important than buoyancy forcing for the mixed layer change?
Yes, the forcing, yes. The wind kicks off buoyancy, buoyancy fluxes and stuff like that. Yeah, at least that's what we're finding, yeah. And I think Luke Rainville also found the same thing in his observations.
Yeah, I mean, there's this sort of competition in the future that we expect maybe surface stress change because of perhaps wind changes, because of ice changes. That's the mechanical change. And then there's going to be the buoyancy change. You mentioned warming, and then there's, the freshening, the intensified hydrologic cycle. And so, which will win? It's kind of an open question. Do you have any thoughts on that?
Yeah, I mean, from the idealized forcing that we did, it seems that wind kind of, plowed through all of the other ones. but that was using NCEP reanalysis forcing bounds, right? So that's current. And so that's not looking at what if the other forcings start to go up. So I would venture, I guess, but maybe don't quote me on this. I think wind would still probably dominate, but I could be wrong.
Hey, Cecilia, I see you have your hand up.
Hi, thank you. This is Cecilia. Can you hear me?
Yep.
Yeah, I just wanted to add to what Mike was saying. Yes, we did find that in some of the regions where we had some decent amount of the data that we collected for that paper, and that paper went only with data up to 2012, if I remember correctly. But what we found was that, yes, indeed, the wind was doing part of this job was the main forcing to change this stratification, the mixed layer depth, but it also seemed to be dependent on what the stratification below the mixed layer was doing. So the wind effect was much stronger when the stratification was not that strong. That I think that's what we concluded there, which probably is not a surprise anyway.
Yeah, I mean, that is what, so one of the advantages to doing high resolution simulations like that is we get tons of information, but the other thing is they can be expensive. So doing a whole bunch of initial conditions or stratification is I'm limited on that front. So yeah, here I'm only doing one initial condition with one initial stratification profile. So my conclusions are definitely limited to that. But yeah, I could definitely see it being heavily influenced by that, by stratification.
Well, I guess the
That's
presence,
right, thanks.
yeah, I would add that the presence of sea ice should also be taken into account, right? Because
Yeah.
sea ice will shield the ocean from a direct wind impact.
Yeah, right. Yeah. So that's another thing is most of my cases are looking at what if the sea ice is gone already. And we just use our sea ice cases as kind of a control, a base case, right? But yeah, having sea ice, having inhomogeneous sea ice all affects all of that too. Sure.
Jamie, did you want to ask a question?
Oh, just a couple. First, great talk. That was really, it sounds like this is really going to develop into something cool. I have a problem though with your very first supposition.
Okay.
That's that the ice buffers the ocean. And I think
it's both ways.
Pardon me?
I would just want to, I think it's both ways. I think the ice and the water both buffer each other.
Well,
if that's the problem.
I guess I wanted, well, you often see that, but if you look at the wind and you say, okay, how much energy can we get into the ocean? I think often, especially unless it's really high winds, you can get more energy into the ocean if there's some ice there. And the reason is the drag coefficient. This is out of your model, but the drag coefficient on a rough ice surface can be a lot greater than it is on a smooth ocean. And you don't need that supposition, right? We all know that what you're doing is important. So anyway, and the other thing is it's a little bit apples and oranges to talk about buoyancy flux versus mixing, because the big part of it is that the mixing is always stirring, right? It's always trying to deepen the mix layer, but the sign actually changes with the buoyancy flux. So sometimes things are working to build a shallower mixed layer if there's negative buoyancy flux. I mean, if there's positive buoyancy flux, I mean, it's trying to deepen the mixed layer if it's negative. So it's a little bit, buoyancy flux is critical to whether the mixed layer is deepening or shoaling, but mixing is always trying to do the same thing.
Any more questions for Kat? If not, then thank you, Kat, again. It was a very interesting presentation. And I think we're ready to start the discussion. That's right, Sam?
Yep, that sounds like a great idea, Dmitry.
So, have any questions for presenters or have any thoughts, comments? Please let us know, right? Please.
Jiaxu Zhang here. So I have a question for Qiang. In your presentation, you mentioned about the effect of the sea ice decline on the oceanic response to the wind stress. And you showed the figure that because of the sea ice decline, there is a increased oceanic stress, which I understand because the sea ice provide negative feedback. But the Ekman response that the map you showed is not very clear to me. So I'm wondering, like, do you see a basin-wide increased Ekman pumping in the response? And do you see any regional distributions, such kind of thing?
Actually, what I would like to address actually is the direction of the Ekman transport from the effect of CI decline. So if you look at the direction, is from the Eurasian basin towards the Maklov basin and the Canada basin. This can really produce the redistribution of salinity of fresh water between the basins. So like in the experiment without any changes in surface freshwater flux and no any changes in the forcing outside the Arctic Ocean, only through change the CS condition by introducing different warming conditions. And then you see that through changing the Ekman transport, there's really big impact on the salinity in different basins. This is a really big signal that actually the observed salinity change over the last decade, the salinity trend in the Eurasian basin, according to our different studies altogether, I think the conclusion is that it's because of CR decline, not through the fresh water, because CR decline always provides more fresh water to the ocean, but we still get salinity trend in the Eurasian basin. That's because of a dynamic effect, the redistribution of fresh water between different basins.
Can I ask a question? This is Mary Louise. This is along the similar lines, I guess. So you showed in the most recent years reduction or a low pressure anomaly over the Canadian sector. But then associated with that, you showed an increase in anticyclonic wind stress curl. Can you explain a little bit better why that is?
Yeah, that's in the forcing field we used. The sea level pressure is low in the Canada basin, but it's even lower around the Canada basin because because the positive AO phase. If you look at the wind anomaly or compute the curl, that's why you have it's in the convergence phase. So not the absolute value of sea level pressure matters, but rather the curl matters when we consider the convergence of upper ocean freshwater. The gradient, the gradient matters.
And he's saying that, I think, that it went down, pressure went down over the Canadian Arctic, but it went down more in other parts. Is that right?
Yeah, the sea level pressure is low, but the gradient is still larger.
Yeah.
Yeah, that means the wind is still stronger. That's why we have this stronger negative wind curl anomaly.
I've got the microphone. I thought that was really terrific, your talk. And what I was struck by, and my mind started to wander because I was thinking about it, but what I saw was you had basically the effect of a positive AO in a case where there wasn't where the ice was historically strong, and you got more of a depression over in the Eurasian basin, and maybe a little strengthening of the Beaufort Gyre. And then you had the case where you had reduced strength in the ice, and that trough extended farther to the east over on the Russian side. I mean, what it struck me as is we see this difference between the EOFs of dynamic topography prior to 1990 and post 1990. And we were just kind of debating yesterday, John Toole was asking about it, you know, is that difference real, or is that just an artifact of the different types of data? But it sort of looked like that could be real in the sense that after 1990, the ice got more mobile, it's less structure there, and your result seems to indicate that you would get this sort of extension of that trough over farther to the east. Mary Louise is looking. If eyes can I can read her eyes, and she's saying, what is he talking about? Anyway, I guess that's a question. Do you think there could be a connection there between the change in the EOFs? You had some EOFs, but you went so fast I couldn't follow it.
Yeah. The point is here actually. The background that this really analyzed in purpose a really short period. It's the same period as you use for the satellite observation. If we do the UF for the long period, the whole period that we have model result, like from 1960s all the run until 2000, 2010s, and the dominant mode is still the Arctic oscillation mode. Although the detailed pattern different, but we will still get that. And the second mode is different from the second mode what I get with this for the short period. That rather featured a dipole mode representing the dipole mode, the dipole mode in the atmospheric circulation. We know the first mode is AO, the second mode is the dipole circulation in the atmosphere. And if we do the UF for the long period, the ocean circulation, the second mode in the model result largely represent the second mode of the atmospheric circulation. And when we use a really short period to do the UF analysis, and actually it's not, if the short period is too short, it really cannot reveal the mode representing the long-term variability in a way. But the point here is not to actually maybe not to reveal the mode as a main purpose, but rather to illustrate the importance of the CI's mediation on the momentum transfer. Because what I want to address that the mode we get, we try to explain the ocean circulation mode or variability in terms of the wind variability. By doing this extensive experiment and do the same UF analysis, my main purpose is just to address that the mode we get from the model, or even in the real world, I would say, is a result of a combination effect of wind and the changing sea ice. But the details of the UF, like you mentioned, I'm not sure, because the result what I get is in details different from the satellite based satellite analysis in your paper, especially, for example, in the Eurasian basin. It's a little bit too strong in the model result. It can be because of model bias. The second, it can be because you use spring data, I use annual mean data. I use the whole Arctic domain, and you use only the Arctic basin. See, I'm not sure about the detail, but that's not what I want to address anyway.
talk about it some more.
Hi, this is Marian Alberti, and I had a question for An. So in your last slide, you had your first point was about constraining the model parameters for circulation and mixing. And I was wondering if you could elaborate a little bit more on what you mean by that exactly, and then what's the kind of information about mixing that's valuable for you in order to better constrain all those different non-unique solutions that you were showing.
Yep, thank you for the question. I think when we think of running a numerical solution, a numerical model, we have the equations for, the Navier-Stokes equations for the momentums and the tracer conservation equations. So there are inputs to these equations. That's what the models are solving for. So they are solving for TNS, but they require the input to be the parameters. So that's what I meant by trying to estimate those parameters so that we would then be able to achieve the output being the TNS to match with the hydrographic observations. So ideally, we would have liked observations of the mixing, of some kind of mixing parameters themselves, right? So then we actually can put them into the equation in order to solve for hydrography. But often it is the case that because the mixing, the parameterization, the parameters of the parameterization is not so easy to observe. So often what you get is you actually observe the output, and then you have to invert for the input. And if you have an input, so you can imagine in a case where if you only have a single value for mixing into your tracer equation for temperature and salinity, then you're using a lot of data to invert for a single number. So that could potentially be a overdetermined problem because you have a lot of data to invert for a single number. But there are evidence that mixing for the entire world ocean should not be parameterized or should not be used just in a single number, but it should be depth dependent. And for example, the turbulence level energy is different at different latitudes. So you would then deduce that it should also be latitudinal dependence. It should be topography dependent because it's related to, for example, baroclinic instabilities induced turbulence as you get close to the coast. So then you have a three-dimensional field for mixing that you have as an input to the model to try to actually solve for the TNS that you observed, right? So then now the problem becomes that if you have not only one mixing parameters related to, let's say, from the parameterization of eddy stirring, but now you also have the eddy, the diapycnal mixing. And then we also probably want to understand something about the energy dissipation related to drags on the side and the bottom. So you would have yet another set of parameters that you try to invert for. So now if we have observation only of TNS, then we're actually now trying to invert for these fully 3D various fields that I mentioned. So the problem often becomes what's considered underdetermined, where you don't have enough data to resolve where the differences in the output from the data should be mapped into which space of the parameters you're trying to invert for. And when it's a non-unique problem like that, then actually it could map into various parameter space, and you can potentially still achieve the same answer for the TNS as you observed. So that's a non-unique problem. And the farther you are from, so I think if you remember, I showed the map. Let's say if we're trying to understand the Atlantic water, bringing the heat or the temperature in this case, all the way down to the Canada Basin, we have a constraint at the beginning at the Fram Strait, and now the moment the model is now trying to solve for the next grid box in the next time step, a temperature, it would then try to use some parameters of drag coefficients, of dissipation, of mixing, etc., to solve for that. And then subsequently, it is related to the spatial distribution that you would have this the solution trying to solve for the temperature and salinity to eventually solve for something to be in the interior of the Canada Basin to match with the ITP observations of temperature. So due to too many degrees of freedoms, you could say, on what kind of adjustment you can assign to the various parameters. So you remember that figure I show of the various flavor of circulation and heat and temperature distribution you could have in the Arctic to eventually still arrive at some set of TNS that could match with the observation of TNS downstream. So ideally, then to go back to the question of what kind of observation. So I think if we cannot obtain direct observation of the quantity we're looking for, which is some kind of parameter constraint for the dissipation and the mixing, then hopefully at least the TNS condition closer to the upstream so that we can actually have invert for the parameter more close to upstream, so that eventually we have a better understanding maybe of what the circulation and what the mixing should be by the time it gets downstream. I hope that answered the question.
Yeah, I guess I'm wondering, can we use like our, for example, for like the diapycnal diffusivities, can we use our theoretical understanding of what the potentially vertical structure of that looks like to help reduce the number of those non-unique solutions that the simulation comes up with? Or like, can you, or another way of thinking about this is, can we look at the range of mixing parameters that those non-unique solutions come up with and say, okay, well, physically, we understand that this version of the diapycnal diffusivity that the model requires to achieve this particular solution is non-physical or non-realistic, and we can throw out that solution? Is there space for kind of either of those two types of approaches in this problem?
Yes, in fact, actually, as you know, normally for such a problem of inversion like this, we have to start with an initial guess of the parameter so that the model can at least make the first, pass the first run. And typically we try to then resort on the literature, we research the literature on what kind of range of mixing we are seeing in the different oceans. And then we try to account for it, maybe depth dependent, maybe topography related, and hence near topography. So you start with an initial guess that is based on, as you said, they rely on something like that. We could, what we have done also, for example, is to invert for using a 1D column where you can say, okay, we have this kind of stable stratification or profile of hydrography, what kind of vertical mixing you need to sustain that. So you could start with something like that. That's right. And that's what we start with. And even the range of adjustment that we make, we also have to make sure that it is within the bound of the physical space. But actually the bound of the physical space alone might still be too wide already or too strict already, because if we don't really have a good estimate of how much we can adjust, then you could end up with two problems. One is that if you make the array, the range over which you can vary too small, but your initial guess is wrong, you are restricting yourself to always be in that. You're no longer allowed to actually be approaching what potentially could have been more realistic because of the allowance is too small. On the other hand, if you don't think you know it well, then you make it, then you have to allow for the adjustment to be bigger. But then now, obviously, you also potentially have a risk that you can actually make, you have a wider range of adjustment. And sometimes if the data you observe for, let's say, hydrography, for example, is not most sensitive to the parameters you think is actually responsible for the physics due to other aspects. For example, the advective timescale might be faster than the diffusive timescale. And therefore, if you have an estimate of refraction contribution, it might actually try to map the correction for the parameters into the space that is related to advective fluxes rather than diffusive. And therefore, you might not make the adjustment to the parameters that you think should be the most appropriate physics. And therefore, you might be stuck at your initial condition. And the moment you're stuck there, often then, as you know, the model is solving for every time step, every grid point using your initial guess or your correction for that parameters. And so that's how, for example, model drifts happens, because if that estimate is not well constrained, then you can potentially have the, the solution will now be rely on that for mixing locally. Does that help?
Yes.
Yes, you're getting a yes.
Go ahead.
Just a quick question. Hi, Ann, this is Ron. Just a quick.
Oh, hi, Ron.
Hi. So just a quick. You mentioned ice drift, and are you now able to assimilate ice drift and at what scale?
Yes, actually, sorry, Ron, probably there was a poster yesterday by the postdoc of Matt Maslov, and working also with Patrick and supposedly with me as well. Actually, I think for the dynamics of sea ice, due to the complexity of the rheology and the, dynamics, we are also testing the capability through machine learning to see whether we can, we can have better stability compared to adjoint, because the adjoint for the CIs, I actually didn't go into detail, but there's the thermodynamics component, and then there's the dynamics component, and the dynamics is a lot more unstable. So we are still, when I say ice drift, actually I did it more in the sense of trying to invert for something that is more still too simplistic, like a drag coefficient, rather than using the second degree, deformation parameters, for example, to try to estimate.
I did see the poster, and I was just wondering how you were going to use, what your strategy for actually capturing, not assimilating the drift into your state estimates. Was that?
You mean how to use the information
Yes, yeah.
gained from
Correct.
from
that sort of predictive scheme that was presented in that poster?
I think I might even refer to Patrick for this, but I think one way we can think of is to use the information to then see how we can improve the parameter space within the CI's rheology or the dynamics parameters. Maybe Patrick, you might have more insight as well.
Well, no, it's really very much work in progress. So we're really learning how to use it. So it's not much beyond that poster that we can say right now.
So for now, Ron, actually, I used a lot of the info for the dynamics of sea ice in the post-assessment sense. But I have not yet gotten to the second order statistics of deformation. So it's still at the basics of trying to understand the drift, just because actually the drag coefficient alone affects quite significantly the upper ocean velocity. I think you also saw that in the previous talk as well. But we are trying to see how we could make use of the high resolution data to understand the statistics of the deformation. And then following that would be, so it's still in development, as Patrick said, but then trying to map that information somehow to the parameter space within the CI dynamics parameters.
Right. Thank you, Anne and Patrick. We have a couple more minutes. We need to wrap up, and to finish our discussion, I have a general question to all the presenters. Have you looked at the Atlantic water circulation? How does it agree, disagree with the classical pattern of the Atlantic water circulation in your simulations? Anne, Qiang, Liz.
I think I will leave the space for others because John presented already what is in Aster.
The circulation mode of the alternative water layer, for example, in the 1990s, we can really see in the at least our model simulation, the stronger cyclonic circulation in the alternative water layer. More warm water can penetrate into the Morison basin from the Eurasian basin. And also the warming trend, as I show in the recent years, as observed. At least in our model simulation, we can get what we expect. Maybe not the detail. If you really compare the details of at each location, the possible observation for temperature salinity, I believe there's certain bias there, but the large scale pattern is well represented. We can see the signal from surface in the wind. Also, we can see the signal from upstream, from Nordic Sea and North Atlantic. Like the temperature signal, for example, we can certainly see in the Arctic Ocean.
All right, thank you. Liz, you haven't looked at the Atlantic circulation, did you? Have you?
Yeah, I honestly haven't really looked much at what the circulation looks like. I mean, I've mostly looked at temperature salinity, which looks about how it should, but I haven't looked closely at circulation patterns to see how they compare.
All right. Well, thank you, everybody. We're going to end the discussion there. Okay, so we're going to get started with our next session here. Patrick, would you like to introduce our speaker?
Sure. I wasn't sure whether I should do this being remote, and I don't have a good sense of the room, but so our next speaker is Dmitry Dukhovskoy from NOAA NCEI, and he will talk about the large-scale mesoscale ocean circulation in their HICOM 2.3 size 5 simulation. Please take it away.
Yeah, thank you, Patrick. Hello, everyone. So I'm going to continue presentation of the HICOM size simulation. So Liz Douglas already gave an introduction of our work funded by the ONR. In this work, we are trying to improve simulation techniques and improve the forecast capabilities of the GOFS, the Navy operational forecast system. The work is still in progress. So I will present several validation results. So we already discussed the observing system simulation experiments. Oh, my fonts is a little bit funny here. They look different in my computer anyway. So OSIS, the idea is to use nature-run simulations, high-resolution nature-run simulations, and then sample them and use in the forecast system, trying to understand the flaws and to improve the assimilation techniques. With main idea, keeping in mind to use in the nearest future new types of observations that should be available in real time for operational forecast, such as sea ice thickness, snow cover, and also observations from the new type of autonomous vehicles that will be or currently being launched in the Arctic Ocean. This is the model domain of the Arctic Ocean, regional Arctic Ocean, HICOM size version 5. And some characteristics are listed in this slide. The ocean component is hybrid coordinate torsion model. Sea ice model is Los Alamos sea ice code size version 5. There are 41 hybrid vertical levels, and most of them are packed in the upper several hundred meters to improve the representation of the upper ocean. There is Greenland runoff from Bamber data, and also monthly runoff from UCOR NCAR data set. All right, so on the right is the grid spacing for the coarser configuration that I will be also referring today, and the higher resolution nominal 25th degree at the equator. But the resolution is it changes with latitude in Heimbach. So it's less than 2 kilometers in the central Arctic Ocean, and it's about 2.5 kilometers in the subpolar seas. And I would also like to take a chance and to discuss a little bit what we understand, say, in high resolution models, because we like to call our simulations high resolution, but what does it mean, high resolution? So it depends on what kind of process we are trying to represent in terms of, first of all, spatial scale, of course, temporal scale, and sometimes on the location in terms of latitudes. For mesoscale circulation, the first Berkeley-Crosby radius of deformation has been used as a scale, length scale. And on the left, I'm showing the first Berkeley-Crosby radius deformation. I calculated it from the quarter degree NOAA World Ocean Atlas 18, and this is winter season. And as you can see, in the central Arctic, the Crosby radius of deformation is about 10 kilometers, maybe slightly less, but in the Nordic seas, it is less than 10 kilometers. And following the definition of an eddy resolving model, I would say that a high resolution simulation would have at least 2.5 kilometers in the deep Nordic seas, around 4-5 kilometers in the deep Arctic Ocean, and much smaller or much finer grid over the shelf in the order of 1 kilometer. And you can see that the first Berkeley-Crosby radius is very latitudinal dependent. So what is coarse resolution in the Arctic Ocean may be very high resolution in the lower latitudes. So unfortunately for the Arctic Ocean modeling community, we really need to have high resolution models. So what happens if the model is not high resolution? What does it mean? We are not going to have eddies. There will be eddies anyway, but what will happen, we will be missing a lot of small scale mesoscale features, and the eddy activity will be low in the simulations. For example, on the left, I'm showing the relative vorticity field from the coarser resolution model, about 4 kilometers in the Arctic, and on the right is the high resolution simulation. And you can see that there are still eddies in the model on the left, but the eddy activity is notably weaker in the coarser resolution case. So that's especially in the regions like Fram Strait and shelf seas. Yeah, you can see the big difference in the eddy activity in the high resolution versus coarser resolution simulation. All right, so let's talk about some validation that I performed with a new configuration of the model. On the left, this is the mean surface velocity vectors from the nature runs. On the left is the Arctic Ocean. On the right is subpolar North Atlantic and Nordic seas. And you can see that the major mesoscale features are in the model. So we can see the Beaufort here, the transpolar drift, and in the Eurasian basin, there is a cyclonic circulation. And in the subpolar North Atlantic, we can easily identify the boundary currents and Labrador current, the East Greenland current, and the northeast flow of the North Atlantic water. These are the mean sea surface height for winter and summer months, with a local maximum in the center of the Beaufort Sea, which signifies the Beaufort Gyre, and the negative SSH in the Eurasian sector of the Arctic Ocean, which is due to the predominantly cyclonic circulation in this area. This slide shows the transport estimates from the 4 years of the simulation. And in the gray fonts with blue numbers are the observational estimates. So I can see that the model nicely follows the budget. The inflow equals the net outflow through the North Atlantic boundary. And there are some questions in several openings. For example, the Fram Strait estimate is a little bit low compared to several estimates derived from observations. Also, the flow through narrow strait seems to be higher than what observations suggest. And also, I looked at the ratio of volume fluxes through Canadian Arctic archipelago, and it seems that the model doesn't pick this up correctly. For example, the fraction of the volume through John Sound is lower than it should be, according to observations. So we are still looking into this, trying to understand if it is a bug or it's just the observations are not correct. Well, I'm kidding, of course. This is let's look at the Atlantic layer simulated in the model. On the left is depth of a maximum temperature, and the Atlantic layer is defined as the zero temperature surfaces in the subsurface ocean, so the below the mixed layer. And on the right is the same map, but from the GDEM version 4 climatology. And the contours, they're a little bit noisy, but hopefully you can read some numbers there. This is the potential density at the depth of the maximum temperature. And you can see that in the model, the potential density shows that the Atlantic layer becomes less dense, at least at this depth, especially in the central part of the Arctic Ocean, which we don't see in the GDEM climatology. And I think that John Toole presentation 2 days ago also showed similar results in agreement with HiCam size simulation. The density was decreasing as we move into the Canada Basin. So which suggests that Atlantic layer becomes fresher. This is the what is this? Heat content density in gigajoules per meter squared. On the left is the model, on the right is the GDEM climatology, and we see that in the model Atlantic layer becomes colder as expected, but GDEM climatology seems to be much colder than the simulation. And we can see this even better in these profiles. On the left is temperature profiles. Upper row is model. The bottom low row is GDEM climatology. I'm showing July. And on the right is on the right is salinity. Yeah, ignore this. It should be salinity, not temperature. And we can see that in the simulation, indeed, the Atlantic layer is notably warmer than the climatology. So we question whether the climatology really represents correctly the temperature in the Atlantic layer in the Canada Basin. The mean circulation of Atlantic water in the model looks way more complicated than the classical pattern shown on the figure on the right. But still, we see that in general, the Atlantic water circulates cyclonically. It flows along the continental shelf break here, and it flows into Canada Basin. But at the same time, I see several disagreement with the classic behavior. For example, here the flow branches into two parts. The one crosses the Gackel Ridge, and the other one continue flowing across along the continental slope. So I don't know if this is real or not, and I couldn't find any validation results to prove this. Next, I'm going to switch and talk about high resolution process on the shelves, and specifically I will be talking about Southeast Greenland shelf. There is very interesting dynamical features in the ocean there. So I will be talking about East Greenland coastal current. As you can see on the Southeast Greenland shelf, there are three jets. One is the East Greenland coastal current, which is very fresh water, which flows very close to the coast, and the length scale, width scale of this flow is very small, in the order of 10 kilometers, well, 10 to 40 kilometers. Many models do not represent this feature correctly. And then the next stream is the East Greenland current, which follows the continental slope, and further offshore is the Irminger current. The east, well, actually, I was showing on the left the coarse resolution simulation and the high resolution simulation on the right. And actually, I was surprised that the coarse resolution simulation was able to pick this up. So the East Greenland current is in the model there. I may be wrong, but I think the first observation which discovered this Greenland coastal current was in 1997, and it was described as a southward flowing jet, described by Bacon et al. In the paper in 2002, and it was further described and characterized in follow-up papers by Pickard and Sutherland and Pickard. It is a low salinity, high velocity jet with a wedge-shaped hydrographic structure. The dynamic of fresh water on a Greenland shelf depends on the origin of fresh water, as well as its position on the shelf. For example, the East Greenland current is driven by thermohaline gradient between the Arctic Ocean and the North Atlantic, and the large-scale curl of wind over the Nordic seas. The East Greenland current is a typical buoyant plume on a shelf. It's wind-driven buoyant plume on a shelf, and its dynamics can be explained in terms of the buoyant plume theory on a shelf. As you know, the East Greenland shelf impacted by very strong downwelling winds, especially downwelling favorable winds, especially in winter. And when this happens, the freshwater jet is pushed towards the coast, the so-called Ekman straining mechanism, and this results in an almost vertical orientation of isohigh lines. And we observe the plume front becomes very steep, this one. In this case, the plume becomes bottom advected plume. In the opposite situation, when the wind relaxes, the fresh water flows on top of the more dense shelf water, and it is surface advected plume. So let's look at the simulation. At the top is the coarse resolution model, and the bottom is the high resolution version, the nature run, and the colors show salinity. The black contours are isohigh lines, and I hope you can see the dashed gray lines. These are the northward velocities in meters per second. Negative means that the flow is southward. And we can see that in the coarse resolution model, there is some indication of the jet, but it's much weaker. Here velocities is in the order of 40 centimeters per second, whereas in the coarse resolution, it's only 20 centimeters per second. And there is a huge difference in the salinity gradient between these two simulations. Comparing to the observations, I would say that the high resolution simulation looks very, very similar to what was observed in 2004. I'm sorry, I'm showing this section at the OSNAP section, very close to the Cape of Fayval. It's shown here. But in winter, yeah, so in the summer, I was showing the summer in the previous slide when there was no downwelling favorable winds. But in the winter, when the shelf is impacted by very strong downwelling favorable winds, we can see the orientation of the isohigh lines are very steep. And actually, the two simulations look very alike. And the interesting thing is that in the high resolution model, we do still see the East Greenland coastal current, whereas it is absent in the coarse resolution simulation. And I'm afraid I'm running out of time, so I just quickly tell you that what this Huff-Miller diagram shows. It shows the salinity change at the bottom of the shelf. So during strong downwelling events, we see the freshening of the bottom layer, whereas during the summer, the bottom layer becomes more saline, which is obvious because the plume is more restricted to the surface. And with that, I'm coming to the summary. So I presented some results from the new setup of the Arctic Ocean high-concise model. This model is used to generate nature runs for the GOVS system. Compared to the course 008 degree, honestly, I didn't see big changes, big improvements for the larger mesoscale features, but I do see big difference in the representation of the dynamics on the shelf, especially the plume dynamics in the high resolution simulation versus the coarser resolution simulation. I didn't talk about this today, but there are challenges in the new setup of the high concise model. The flow structure in the narrow straits channels still doesn't look quite similar to observations, the Bering Strait and Canadian Arctic Archipelago channels. And CIS, we had lots of troubles with CIS 5, but I think we were able to make it work. Thank you for your attention. I'm open for questions.
Great, thank you very much, Dmitry. I cannot see the room, so maybe someone else should call, or maybe Dmitry, you should call on questions directly.
I think we actually have to move on to our next talk because of time.
Okay.
The discussion.
Okay, so then our next speaker is Elizabeth Fine from UC San Diego, and she will present an Arctic Ocean circulation and water properties in an ultra-high resolution global model.
Okay, great, thank you. So I'm Effie Fine. I'm a postdoc with a split appointment at Hui and Scripps, and I'm presenting work that I've done at Scripps with Julie McLean and many other collaborators, some of whom are listed here, which was supported by the Office of Naval Research and the Department of Energy. So for a little bit of motivation, I think we're all aware the Arctic climate is rapidly changing, and we're seeing that signal both in declining sea ice and a warming ocean. And the climate system is also sensitive to Arctic changes. I'm especially interested in some potential feedback loops. Okay, thanks. No problem. All right, yeah. So I think the kind of ice albedo effect has made it into the public consciousness, where less sea ice means the ocean is exposed to solar forcing and it's darker than sea ice, so more heat is absorbed and that warms the water, which can melt more sea ice. But then there are these two other, kind of ocean-mediated feedbacks, which Kat set up really well and went into way more detail on her talks. But basically, there's potentially a wind, ice, ocean feedback, where less ice could arguably result in more wind energy getting into the upper ocean. And because the Arctic Ocean is salinity stratified, if there's more mixing in the upper ocean, that can move heat up from the ocean interior to the surface, resulting in then melting more ice. So this is also a positive loop. And then there's kind of a convection-mediated ice brine rejection feedback, where less ice results in more ice freezing. So then you get more brine rejection. And then that brine is rejected, sinks, and results in, again, a deeper mixed layer and more heat flux in the upper ocean, potentially melting more ice. So these two are different mechanisms, but they have a similar effect of deeper ocean mixed layers, bringing more heat up from below. And so this all brings us to this nature run, and so Liz and Dmitry have discussed a bit about this collaboration between Scripps and Florida State University and NRL, where we're trying to optimize Arctic observational sampling strategies
And I'll just be discussing this one nature run using the POP model. And the idea here was to use an ultra-high resolution model so that we could capture mesoscale Arctic dynamics. So I will go through a little bit about the model setup, and then some of the work we've done just to assess model realism and how well we are capturing things like sea ice, the circulation in the Arctic and Arctic hydrography in this model that we're hoping we can treat as nature. And then I'll go a little bit into what kind of some of the implications of the biases that we're seeing in this model are for understanding the ocean ice system in terms of the upper ocean heat content and stratification and the possible effects of that on sea ice. So for a little bit about the model setup, this is a specialized ultra-high resolution grid that scales down to 2 kilometers at the poles, starting with 8 kilometers at the equator. So you can see the resolution in the Arctic. Most of the central Arctic is in the kind of 2.5 to 3.5 kilometer range, with slightly lower over the shelf seas. The vertical levels, so it's a 60 level Z grid, and the vertical levels start with 10 meter bins at the surface and then vary down to 250 meter bins at in the deep ocean. It's a POP model, and it's run on this special tripolar grid to really maximize the resolution over Greenland and the Arctic. It was set up, used for actually a different experiment, was funded by the Department of Energy. And then for this project, we used the JIRA 55 forcing and initialized it from a GOFS run. And so we have a spin up that started in July of 2016. And then the thing we're treating as the production run happened from 2017 to 2020. And oh good, my movie's playing. So just to get a sense of the kind of mesoscale dynamics we're hoping to see here, you can, this is just speed that's looping through in a movie now. And you can see there are these boundary currents and then some really nice fine structure features in those currents. And you can actually see the seasonal influence of the sea ice on ocean speeds. So when it's ice covered, things are kind of larger scale and slow. And then when the ice breaks up, you get these really higher resolution eddying features. So getting a little bit into the model realism. So one of the first things we looked at is sea ice. And in general, what we find is that the total sea ice extent agrees well with observations. So here the model is in red, and 2 different algorithms for assessing the sea ice extent are the black and dash black lines. And it's just in the summer where the model has a bit of a bias. So we're losing summer sea ice faster, but then recovering it again in the autumn. And if we look at spatial maps of ice concentration, we see kind of similar things. So the ice concentration looks pretty good in April we have observations on the top and model on the bottom. In September, we've just melted too much ice. We have low concentration everywhere. And then in November, the extent is looking better, but you can see the concentration in the model is still pretty low, especially in the Eastern Arctic and in this area over the shelf seas. So that's a bit of summary of what we've seen in sea ice. We looked at Arctic circulation as well, so it's hard to get a good observational product for surface velocity. So we're using the ASTI reanalysis, which Anne talked about, the polar gyre state estimate. And that ran through 2017, and 2017 was our first year of the model run, so we're just comparing that 1 year. And I also just have this current schematic from Eddie Carmack's paper. And so the kind of big picture, we do see circulation that outlines the major Arctic currents. There's inflow in Fram Strait. There's this boundary current that's associated with the Atlantic water flowing around the basin. You can see the Beaufort gyres, anticyclonic circulation is in here. And we have a signal of the transpolar drift. Comparing to ASTI, so we see there are larger velocity magnitudes in the POP study, and there's also just more eddy variability with these smaller scale arrows going in different directions. I'm not sure that we're really concerned about either of those. We're running this at high resolution, so it might make sense we see more energetic boundary currents, and then of course this more mesoscale activity. Getting into hydrography. So this is the same section across the Arctic that Dmitry just showed in his model. So we're have Alaska is on the left-hand side of these plots, and then they go through the North Pole and down to Iceland. On the top, I've got our model output, the POP sea ice model, and then the panel beneath that is the World Ocean Atlas, and then the lowest is the difference, so temperature is on the left, salinity on the right. And overall, the structure looks pretty good. We have this salinity-dominated stratification with surface waters, especially in the Western Arctic, that are cooler than the deep ocean and fresher. We have the Atlantic origin water that comes in on the eastern side of the basin and then is found deeper in the Western Arctic, as well as cooler. And we have the signature of the cold and fresh Beaufort Gyre with this cold halocline in the Pacific, where fresh water accumulates. You can also see there's some biases in the model. So the Atlantic water in the model is warmer than the climatology. The salinity gradient in the model is weaker than what we see in climatology. And so that means also that the stratification is weaker in the model. And it's a little bit hard to see in this climatology. There's this slight temperature maximum in the Western Arctic that's associated with Pacific summer water. And that's essentially missing in the model. I'll go into that in a bit more detail later. And we had the same question about, is the climatology accurately representing the most recent years, since that's a compilation of data over a couple of decades. And so to try and get at that, I pulled data from the ice-tethered profilers. So there are about 25 drifts in this period from 2017 to 2020. Most of them are in the Western Arctic, with just a handful in the east. And so on the left-hand side here, I've just split this data up into the western and eastern portions, where I'm just defining things that have a longitude to the east as eastern and to the west as western. So that line kind of goes like through here. And we got temperature on the left, salinity on the right, and the model output is in black. The observations are in colors. And so the model profiles here are for each ITP profile. I've gone into the model, pulled out that grid cell that day. So every profile is matched that way. And so what we see is, sure enough, there's this peak in Pacific summer water in the observations that just don't show up in that model profile in the Western Arctic. And we also see that there's a difference in the Atlantic water. In both sides of the basin, it's more dramatic in the east, where the model Atlantic water is a little shallower and a little warmer than the observations. And so we can also look at this spatially. We can look at the depth of the Atlantic water, which I'm treating as the first crossing of the zero isotherm. So the background color here is the model everywhere, and then these squiggly lines on top are the ITP drifts. So you see the observations usually have that a little bit deeper. We can also look at the maximum temperature of the Atlantic water, and we see the same story. It's a little bit warmer in the model, although there's a lot of spatial variation. The Pacific summer water temperature, you see the model does have this warm Pacific summer water signal right near the boundary's edge, the basin's edge, but in the central Western Arctic, it's actually quite cool relative to these ITP profiles that show temperatures up to 1 or 1.5 degrees. And then this doesn't come out in these basin average profiles at all, but we can also look at the winter mixed layer depths. And so here we see that the model mixed layer depths are quite deep relative to the matched ITP depths from the same time. So in summary, just to go over this model realism part, we see that our model sea ice generally agrees pretty well with observations, but there's a bias towards low ice conditions in the summer, and that kind of persists through freeze up, especially in the Eastern Arctic. The velocities reproduce the known current pathways, and I took the slide out for the sake of time, but our gateway fluxes, we looked at the major Arctic gateways, and they're within error bounds on the observational estimates, which admittedly are a little bit large. So there's nothing there that seems obviously wrong, at least. The water masses appear pretty much as we would expect them to, but we have these couple of discrepancies where we have Atlantic water that's a bit warm and shallow. We're kind of missing the specific summer water temperature maximum, and the winter mixed layers are overly deep. And so in the next section, I'm just going to talk a little bit about what the consequences of these ocean biases might be for the model sea ice. So to look at this, I'm starting with one example ITP drift. So this is ITP number 111, which was deployed in the Eastern Arctic in October of 2019, and then it drifted to the south. Well, okay, directions are confusing in the Arctic. It drifted towards Strait, and we ended this around April 2020. And this period includes the winter deepening of the mixed layer, since we're going from kind of fall into early spring. So I have the temperature of the observed profiles here, then the model beneath that, and then on the right, I have just the stratification from observations and model. The bottom's the difference, and then this red line in temperature is the mixed layer depth, calculated as the difference from the surface. So what we see is in the ITP observations, we get this deepening of the mixed layer, but that's separated from the warm Atlantic water below by this kind of cool halocline layer. So even though the mixed layer is deepening, it's protected from that heat by this cool and really quite stratified water in between. In the model, we have Atlantic water that's warmer and closer to the surface, and we also have a mixed layer that gets a bit deeper. And so here it seems like the mixed layer is getting deep enough that we have the potential to entrain excess heat from this warm Atlantic water, which is relatively warm in the model, up into the mixed layer. We can look at a different example. This one's from the Western Arctic, where things are actually quite different. So this is ITP 114. This was deployed around the same time in October of 2019. And this deployment lasted through August of 2020. And so here we actually get both the deepening of the mixed layer and then the summer restratification as the ice melts. So here we find actually in some ways the situation's flipped. So in ITP observations, as the mixed layer deepens in the winter, that's occurring just above this warm Pacific summer water. And so there's this potential for entrainment, not of Atlantic water, but of Pacific origin water in observations. In the model, the mixed layer is deeper, and it actually gets so deep that probably anything that's below 50 meters depth is going to get entrained. But the ocean that it's deepening into is much cooler because it doesn't have this warm temperature. And so the net impact on sea ice is kind of unclear because there's potential for entrainment in both of them, but the ocean beneath is quite different. And so to try and understand, we have these nice examples, but can we draw a bigger picture? So I averaged all these temperature profiles in the upper ocean in both the Eastern and Western Arctic, and then I've split them down into a kind of fall, so this is October, and then a March case. And the one point I want to make before getting too far into this is that the Atlantic or Eastern Arctic drifts, for one thing, there are not very many of them, and also they kind of started around the same point and then drifted through the same area. And so we've had these conversations about we're missing observations in the Eastern Arctic. I think that could really affect things here. We're kind of watching both of them move out of Fram Strait. So I'm treating this as a one-dimensional story, but that kind of a drift in both ITP deployments is wrapped up in that. In the Western Arctic, we have more observations and they kind of drift around more randomly, so it seems more fair to do this type of averaging. Now the numbers here, the top numbers are just the heat content above 100 meters integrated in both profiles. But because it's hard for me to have physical intuition about numbers like 10 to the 8th joules, I also converted that into a potential for ice melt. So these lower numbers are if you take all of that heat and apply it directly to the sea ice, what melt do you see? So that's not what actually happens in reality, but it's a way of getting a little more intuition about what these numbers mean. So what we see is that in the Eastern Arctic, there's more model heat stored beneath the summer mixed layer. So both the models and observations have a relatively shallow mixed layer, but there's warmer water beneath that in the model. And in the winter, as these both mixed layers deepen, but there's the potential to have entrained more heat from the model than in observations. So the change in the potential ice that we could melt between the October profiles and the March profiles is something like 50 centimeters in the model and only 20 centimeters in the observations. And so this is potentially consistent with the idea that we're seeing ice form more slowly in the fall in the model. That could maybe mean that we're actually entraining some of this heat and slowing down ice formation. In the Western Arctic, there's less heat stored beneath the summer model mixed layer because we don't have the Pacific summer water in there so much. And but that model mixed layer gets deeper, whereas in the observations, the mixed layer stays shallower, although there's more heat available. And we actually go through the numbers. So I think I got lucky in terms of what depth I picked to integrate to, but what we find is that actually in this case, the situation for the sea ice above these oceans is kind of identical. There's the same amount of heat that's potentially entrained as these mixed layers deepen, about 40 centimeters per meter squared. So I think this is showing a really different scenario there's a bias in the model. It's not necessarily having any impact on the model sea ice, but it might impact other things that we care about. So in summary, so we have an ultra-high resolution model that largely is reproducing the Arctic circulation and water masses properties accurately, although there's some biases. And I would say that these model biases are consistent with the hypotheses climate feedbacks we've discussed, that the weaker stratification goes with deeper mixed layers, and that seems to be occurring alongside reduced sea ice, at least seasonally. And we have a model of ice field that agrees relatively well with observations, at least aside from that summer season, but the discrepancies in the upper ocean heat content are significant. And I think this poses challenges for some applications. So one of the things we initially were discussing with this when we started this project was that we could use this very high resolution model to understand the dynamics of Pacific summer water and how it's getting into the basin, how heat fluxes might be changing. But if we're not keeping that Pacific summer water over the course of a year, it's really hard to use it that way. And it also makes me wonder about projections for sea ice from a model like this that's not, maybe getting ice right, but for the wrong reasons under climate change. So if we change the forcing, we don't have this huge potential to entrain heat from the Pacific. So yeah, that's all I have. Thanks very much. I can take any questions.
Thank you very much, Elizabeth. I'm not sure. Do we have time for questions, Sam?
I think we need to move on, but we can address the questions in the discussion.
Okay. So I think I'm the next speaker, right?
Would you like me to introduce you, Patrick?
Yeah, or someone at least. Yeah, sure.
Next up, we have Patrick Heimbach from the University of Texas at Austin.
Thank you. Thank you, Sam. I hope you can see the full screen of my presentation.
Yep, we see it.
Great. Well, so I've been giving sort of a task for some general discussion, but I wanted to bring up some very general sort of points, some of them just some sort of philosophical musings. Let me see if I can advance the slides here. I'm not advancing right now. Oh yeah, there we go. So of course, a modeler, and so the goal here is to bring together models and observations, but just to remind ourselves, why do we care about the models, right? So they are the underlying equations of motions are the best shot that we have at peeking into the future through the prediction. And this is both for operational predictions, as was pointed out, interest to the Navy, or subseasonal to seasonal ice prediction, all the way to climate projections. So the underlying equations of motions, they conserve properties globally and locally at the parcel level. So that's even if there's many things we don't know, this is really a strong constraint that we can place on those models. We can also look at them as sort of dynamics respecting interpolator of sparse data. And the Arctic is, we often talk about, big data problems, but at least from an observational perspective, the Arctic remains really a very sparse data problem, so a big challenge. And then, of course, we can use the models to ask what if experiments, and that gets at the fundamental question that we try to understand system sensitivities. We know that these models have ingredients. It's obvious, and many of them uncertain ingredients. Many of them have been sort of alluded to here, but just to remind ourselves, the initial conditions are, of course, uncertain. The boundary conditions, so the surface forcings, we rely either on atmospheric reanalysis that have large, potentially sometimes large biases, or we have lateral boundary conditions from global models when we run regional simulations. And we have basal boundary conditions, for example, topography and other cases. The model parameters are certain. We have parameterization scheme, we have subgrid scale parameterization scheme, and we have constitutive laws. They are, even if we had the model fully resolved, there are still empirical laws to the constitutive laws in our equations. And then there are, of course, structural model uncertainties or model inadequacies when we actually just have the wrong formulations for parameterization. So then, any question or no? Okay, when we then validate models, so of course we will find misfits, right? So now what can we do? So here's a little excursion, right? So when we let's take a simple model. So our simple model is a linear model. X of t is a plus b times t, and we have uncertain data. So these are the observations, and we have uncertain model parameters, right? So the coefficients a and b, so there's a couple of things we can do or we should do, right? So well, the first thing that we so the first thing that we should do is, we learned, so this is a least square problem. We're trying to fit the data in a least square sense. We have these parameters, the slope that we could think of, like if we make the analogy, could think of as model parameter, and the intercept, we could think of it as initial condition, just to simplify things. And a calibration exercise, then, if this is a parameter, would consist in optimizing this parameter b and estimating that, finding an optimal value for b. Or if we want to find an optimal initial condition, so this is the calibration problem, where it's not the initial condition problem. The initial condition problem is this one here, where we know b, but we try to get a estimated, right? And so this problem is actually the one that we have in conventional data assimilation, right? So in operational weather prediction or any kind of, well, most data assimilation operational is we find new initial condition to basically find this optimal fit. Of course, we could do both, right? So in a general inverse problem, we try to estimate, both parameters a and b together, right? So but what I'm getting at is really a purpose is, a value, and the observations, bringing them closer together with data. One is to go beyond just trying to validate the model, but trying to find ways on how we can use all of the different models to get at this problem of trying to find sort of a model that is both calibrated, right? Well calibrated and also well initialized, ideally simultaneously. So, and that, of course, is the purpose of data assimilation or Bayesian inference, where we combine the imperfect knowledge in the model, in the data, in the prior information that we have, for the purpose of either parameter estimation, which is the calibration problem, or state estimation, if that's the reconstruction problem, or the model initialization problem, which is the prediction problem, numerical weather prediction, or the flux inversion problem, right? So we can also think of this if we think of inverting for CO2 fluxes in the ocean or in the atmosphere, where invert for optimal fluxes given interior observations. But then again, data assimilation itself also comes with uncertainties. And again, one of those is the data themselves. They come with observational errors. They also come with representation errors, so scales that the model cannot resolve, but that the data resolve. There's observational sampling. So we have sparse observations. We have inhomogeneously and disparate types of observation. In the data assimilation scheme, we have to approximate the error covariance that are crucial ingredients, and the data assimilation methods themselves differ. So that's always important to keep in mind as we, trying to accumulate all of these different sources of uncertainty. So let's come back to this asking sort of the fundamental question of system sensitivity. Well, so what we've, this panel, the left panel here is potentially a good one, right? So we've been thinking about different parts of the circulation, and I'm not sure whether is it clear, maybe not for me as an outsider, of what the circulation is, right? So in many cases, we think about the before gyre or the surface circulation, which is basically the one here at the top, which is especially locally influenced through to the large scale atmospheric wind field. Then the remote, so when we talk, and this of course affects the freshwater budgets and transports very importantly, right? So the freshwater accumulation in the before gyre, for example, through sea ice melting, through the convergence of riverine water that basically makes its way here, precipitation and so on. So very important for the freshwater component of the system. But then for the heat component, we have other things that we may care about more, and these are different types of the circulation. Atlantic water inflow into the Arctic interior that are remotely forced, right? And its variability is remotely forced. Pacific water inflow, again, sort of something that's remotely forced at a different level. Also, as Mary-Louise showed, also in part, maybe also relatively locally forced in sort of through open sea ice here in the Pacific sector here. But these are different aspects of the circulations that, in the sense that they've been forced through different surface climates remotely on different timescales, and then make their way into as a part of the 3D Arctic Ocean circulation. So this is another picture just basically showing the importance of or how the Arctic circumpolar circulation distributes some of these waters, especially Atlantic water inflow into the interior. And then the question, of course, how those boundary current exchanges its property with the interior through sort of mixing is certainly a very important component here. And so yet another very important aspect of the circulation dynamics, caring about regionally amplified mixing. And so, so can we sort of, looking at the sensitivity, how do we understand these different, sources of sensitivity of the system? So I'd like to point to three sort of through, how can we use, if we had systematic sensitivity information, to understand the system well? And so highlighting here three papers. The one is by Nguyen et al. And that's basically looks at the sensitivity of volume transport through Bering Strait, through changes in surface forcing in space and back in time. And we can do this through the use of the adjoint. So what we adjoint, all of it does, it computes the sensitivity of this J, which is now our transport quantity of interest, to all kinds of, so this omega K can be different forcing types: wind stress, zonal and meridional, freshwater flux, surface air temperature or heat flux, both in space and then also back in time. And so these sensitivity maps can be used as kernels in a convolution. So think about this as a very detailed Green's function, and we can reconstruct in a linear sense this transport variability both as a function of season, that's the top panel here, and also as a function of the interannual variability. And the two main messages here in this is that it's actually, the seasonal cycle, the contribution varies both in sign, but it also varies in its relative contributions. So this is really a simplified version of a figure that Anne produced in this paper, which basically says here the contribution of forcing surface wind stress forcing variability over the Pacific sector versus sensitivity to wind stress forcing over the Arctic and Atlantic sector, right? And so this varies as a function of season, but it also varies interannually, right? So some years the Pacific sector forcing is dominant, in other years, like in blue here, and then in other years, like the one in orange, the Atlantic and Arctic sector actually dominate to control this annual variability. So it's something that it's good to disentangle and trying to actually understand this in the context of observation. Other examples are, see if I can advance my slide here. I think oh yeah, there we go. This is a recent study by Chiro Fukumori and others. They actually do look at the sensitivity of freshwater content changes in the Beaufort gyre and also sea level, and do the same type of sensitivity decomposition by looking at what is the dominant contribution, how can we reconstruct this freshwater content variations as a function of space and as a function of time using these sensitivity kernels, and where again they basically find, very interestingly, sort of a decomposition both of wind stress in certain parts of the region which play an important role. So this is the left panel here, but also the sensitivity to the surface freshwater flux, which also plays an equally important role, and that's related to the meltwater of sea ice that basically plays an important role here, and that can be quantified in quite some detail as space of time. I don't have time to go into this. Another paper here is the one by Bigdelli et al. Of 2020, where they look at what controls winter, the sensitivity of late winter sea ice volume thickness or volume anomalies to early winter or late fall, the previous year, warming events. And what they show here is a crucial role. It's a snow melt conductivity feedback. The importance of melting snow on ice early in the onset of the winter, when you have young ice, sea ice, and have a good snow cover on, and the important role of insulating this against sort of late winter melting, or the fact that this snow gets melted away early on and then basically provides a very different conductive heat flux across the ice interface. So how can we use those sensitivity observations? I'd like to, so that's the last part of my talk, is can we use these type of sensitivity for observing system design? And the answer is that we may be able to, in a slightly different way, on doing observing system simulation experiments, namely using the framework of uncertainty quantification within data assimilation framework. So the uncertainty quantification proceeds in 2 steps here. When we do data assimilation, what we're after, we're trying to minimize model data misfit. That's even here in this first term here, the J observations minus misfit. We have some prior information of some of the independent variables or the uncertain variables that I've mentioned before. And when the curvature of this misfit function tells us something about how well observations constrain that misfit, right? So if the curvature is very large, the observations tell us a lot about reducing that misfit. If the curvature is very weak, then the observations don't actually tell us much about this. And so this can be expressed, curvature, by the second derivative or Hessian information. We can derive Hessian eigenvectors to basically simplify these approaches a little bit, and there's other ways on how to simplify. But now these eigenvectors can be thought of as sensitivity of the observations to all these independent parameters like the forcings. We can then also have a quantity of interest. So this is our J is now, for example, a heat transport across the section, let's say Scotland-Iceland bridge, and we can compute the sensitivity to those, the same sensitivity pattern. So the Q is this quantity of interest sensitivity, the VIs are observation sensitivities, and we can project them onto each other. We can form their formal scalar product, and we can see a degree of shared adjustment mechanisms between those two, right? So if that scalar product is very strong, then that means that the sensitivity to variations in the forcing basically give us shared adjustment mechanisms here. I'm glossing over this as an example here. We have 2 panels. So the left panel is heat transport. That's basically what we're interested in, something that is not observed. Heat transport across Iceland-Scotland bridge. And then to the right, we have a quantity of, I'm sorry. So yeah, to the left, that's the quantity of, and to the right is an observation, for example, in the OSNAP array, Irminger Sea subsurface temperature, just as an example. And we see those sensitivity maps back in time. This is sensitivity of those quantities to changes in the meridional wind stress back in time. And they make over a certain time, and they make physical sense. We can actually interpret these pathways. Why is it that they are sensitive to mineral wind stress perturbations, let's say here off the coast of West Africa, over a certain period of time? And we can now, so these patterns have similarities, and they also have discrepancies, right? So in box 2, these patterns are similar, and so shared adjustment processes if we form the scalar product. But they're also, in this box 1, there are also differences where basically we have, so to speak, destructive interference, and therefore they destroy some of these adjustments. And going through the process, we can actually quantify how much observations reduce the uncertainty in these quantities that we're after. This can be extended to not just one observations, to many observations through some orthonormalization process, where we can then ask the question, to what extent are added observations actually redundant, such as in this case here, in this case, or to what extent are other observations complementary to what we already have. I'm not going to go through this process, just to give another way and to reaffirm the potential that models and certain data assimilation can actually try, at least help us trying to understand the observing system and how the value and the sparsity of the observing system. And so to conclude, and maybe a question to as a part of the larger discussion here, we should try to formulate what we are after in the observing system that we're designing. And it's of course hard questions, and it's okay to have multiple design questions, but it's good to formulate, even if there are multiple of those. Let's try to formulate what it is that we're after. Are we documenting circulation changes that we're trying to as a response to climate change? And then, what circulation is it that we mean? And can we develop compelling metrics for those that would be very powerful? Or are we assessing freshwater storage, transport changes, or heat storage, transports and changes, which are likely as targeting different branches of the circulation? And we, of course, here for the workshop, we haven't talked much about biochemical cycles and ecosystem, but it's, of course, something that we should be mindful of. Those are likely, again, as I've pointed out, potentially different aspects, and they will have to think about different things. And then finally, as been seen in several previous talks, right? So the air-sea interactions are also really important both for the ocean. So having bad atmospheric forcings or air-sea fluxes will give us poor sort of simulated ocean states, but also vice versa, right? So the potential of the ocean to give us to constrain fluxes that are useful for the atmosphere would be important. And with that, I think that's all. I'm happy to take questions or open room for discussion.
Excellent. Thank you, Patrick. Yeah, we can move into questions about your talk and general discussion. And was that, okay, yeah, let's see your hands up.
Sorry, I got the wrong signal. I wanted to clap.
Okay. So are there any questions online or in the room? Mary Louise?
Thanks, Patrick, and thanks to all the speakers. I'm not sure if I have a question for you, Patrick, or for everyone, because a common theme of the different models appears to be a too warm Atlantic water layer, and I'm wondering if there are any sort of agreed upon hypotheses for this, and how you would go about rigorously diagnosing why that might be. We could start with Effie if you like, or Dmitry.
Yeah, so that's a great question. We do have, I don't know about different models and why they have this problem uniformly, but in our model, a couple of the things we've looked at. So one is the initial conditions. The initial conditions already had Atlantic water that was a little bit warm. That was from Goff's. So that is just like, it came from a different model. there's also a signal in our model of that Atlantic water getting warmer, and there's actually a kind of big spike in 2018 where it gets much warmer. And so Julie found with some observational work and then looked in the model, so in the subpolar area, like in the Nordic seas, there was a warm temperature anomaly there that was actually observed in 2017 and is in the model. And so our kind of working hypothesis is that there might be water that was too warm, or maybe even accurately warm, that came through Fram Strait, but then maybe something about the circulation, either we're moving it through the Arctic too quickly and there aren't very many observations in that region to know, like there might be a real pulse of Atlantic water that's warm that we just haven't seen, but it's moving in faster in our model than in reality. Or the other thing that we've thought about, but I'm open to ideas on how to rigorously diagnose this, is if we don't have kind of like eddy processes that move heat out of Atlantic water, or let some of that heat be lost to the atmosphere as it's circulating into the basin. I think that's possibly a reason why it might be increasingly too warm over time.
Just to add to what Effie was talking about, indeed, most simulations indicate that Atlantic lay is warmer than it is in the climatology. My hypothesis is that climatology doesn't really reflect the most recent changes in the Arctic Ocean, because we know that climatology always lagging in time in processing the data that were available. So the way to validate this is to look at the ITP profiles. I think this is a great source of information which hasn't really been used yet, at least in our case. And I think Effie starts doing this. And I know that World Ocean Atlas will be released soon, which hopefully will be more realistic. So.
Yeah, I think I didn't make a big deal about this in my talk, but we did that comparison with the ITPs, and so we find that the ITPs are kind of between the climatology and what we see on the model. So it's like some of it is just that the climatology is too cold, but then also there's something in the model that's not agreeing with the synoptic observations.
Okay, I think Visa, you had your hand up first.
Yes, I wanted to follow up on a question from Mary Louise, and just mention that we might be dealing with two issues here in terms of potential biases of the Atlantic water being too warm. One thing is that input of the Atlantic water through the gateways, the Fram Strait and the Barents Sea in particular, again, it's something that vary across different models, but I would emphasize again that it's still relatively poorly constrained based on observations. Another issue we're dealing here is a fully coupled problem in terms of air-sea interactions, where the Atlantic water is removing a lot of heat to the atmosphere before it enters and sinks underneath the ice. And when you have the ice-ocean force simulation with the reanalysis, you are not allowing for this feedback back into the atmosphere. And even if you try to remove some of the air, some of the heat from the surface warm waters as they're moving northward, the atmosphere doesn't know about this and still is forcing your ocean and sea ice as nothing happened. Thank you.
Anne?
Yeah, perhaps I could follow up on Wislav's point as well on the feedback. But I wanted to mention first on the climatology. So in the Canada Basin, I think the World Ocean Atlas version 2013 version 2 and 2018 already took into account ITP data. But if you recall again how these products are produced, they were, optimally interpolated based on the availability of data, for example. So you can imagine, for example, if it started from the PHC and the older, not PHC, the older temperature salinity from the 50s up to the 80s or the 90s, right? So at that time, the Arctic is generally understood based on the data from the climatology as being cooler than present. And now you have a new data set that is more focused in the Beaufort Sea from ITP. So then the new climatology will then have a warmer Beaufort Sea. But if it does not have enough data to also update the data in the Eastern Arctic, you now actually have a product that might still be biased in the Eastern Arctic, but now more up to date in the Western Arctic. So if one were to try to use that to constrain model mean temperature salinity, so the first thing, maybe you get the false impression that you're too warm in the Eastern Arctic because the data have not gone up to date to be consistent with the Western Arctic. So if you try to adjust to that, then obviously you will end up actually with warmer temperature subsequently downstream. If you were to follow, for example, some pathway of Atlantic water imported in, and if you are now trying to adjust for a cooler temperature in the Canada Basin, then now you actually do something in your model that is now physically inconsistent somehow to try to adjust for the flow so that it fits with the older climatology in the Eurasian Basin and fit with a better climatology in the Western Arctic. I'm not sure if I communicate across clearly, but so it all boils down to answer Marie-Louise's question and maybe address some of the coupling issue that Wisław mentioned. Without the observations that are consistent, as you can see, there are just too many unconstrained pathways for you to figure out if you are to understand based on the conservation equation, based on the physics. Let's say you have the tracer conservation equation of temperature, so you have an understanding, you need to ventilate whichever way, how much is advective fluxes versus how much is diffusive and SE heat fluxes, etc. But without the observations, you can see there are just too many degrees of freedom to really be able to track every grid point to eventually arrive at a single location of a profile, for example, and try to match that. And so it becomes a complex problem if that's what we are trying to do. Then it's not. I don't know whether we should answer the question, why are model too warm in the Atlantic water inflow if we don't have a metric or a way to to have constraints, to have better constraints so that the various adjustment as heat flux for fully couple or feedback to the reanalysis or adjustment in parameters.
Mary Louise, I'm sort of surprised that you led with the Atlantic water, because what I also noticed and what was pointed out by Effie and others is that the models have trouble getting a nice summer Pacific water temperature maximum. And why is that, do you think? I know that, I work with Jinlin Zhang with biomass, and it bugged me that he wasn't able to do that. And so I think actually Mary Louise is a co-author on this one paper where Jinlun did some magic tuning. I think it was shortwave radiation absorption, and I'm not sure exactly what else, but somehow we managed to get, in that particular simulation, a pretty good summer Pacific water Tmax, but I know that it is generally difficult for many models. So here, I'll just hand it to you, Effie.
Okay, yeah, this is another one that I've wondered a lot about. I think there are kind of two things that I can point to, and they're related. And so one is, I think our vertical mixing is potentially too high, and the other is that our stratification near the surface is too low. And that a bit of a chicken and egg problem, right, where we have the weak stratification lets the mix layers get really deep, and the high mixing keeps the stratification low. And so it's difficult with one model realization to say exactly physically what's causing that, but I think that those problems are really related. And I think it doesn't surprise me that if you were carefully tuning a model to make sure that it was right, you can probably very things like this and get it to work out. But I also think Erica Rosenblum has a paper where in some of the CSM runs, you see a very similar problem. So I think it's not just our model that has that kind of issue.
I think, John, you were lined up first there.
Yeah, one thing I've been worrying about is all of these models, as they get more and more horizontal resolution, they all seem to have 10-meter vertical resolution near the surface. And maybe we need 1-meter vertical resolution to clearly demark that these very thin layers that aren't mixing very much.
Yeah, I forgot to say that. We also worry about our vertical resolution. I mean, the actual mixed layers are very thin and the stratification changes very rapidly on scales of, like a meter or half a meter. And we're definitely not resolving that with 10 meters.
I would just say that I know at least in Effie's model, they use KPP, and KPP is extremely resolution dependent. And so whether or not it gets things, it's highly tuned for certain resolutions. So there's a moment or an inertia in terms of changing vertical resolution as well. Not that that means that we shouldn't, just saying. Yeah.
I need to double check, but I think in Heimbach we have pretty good resolution in the upper ocean. If I remember correctly, in this configuration, the first layer is one meter thick, and comparable thickness in the layers up to several tens of meters. I haven't checked this yet, but now I will be surprised if I do have some Pacific water in the simulation.
Anne?
Yeah, I wanted to maybe address back to what Patrick was mentioning, trying to understand the physics first before, so for example, I don't know if many of you remember back at the beginning of AOMIP when Greg Holloway was comparing all the models, and they all have quite systematic issues. And one of them, for example, is the missing halocline in the Western Arctic. And the key there is whether actually is the process to produce that particular water mass is available. And then you can then look at the tracer equation again to see what kind of force balancing in there. Then if that signal is available, how is it destroyed? But sometimes the process might be missing as well. And then it could now then be related to horizontal, vertical resolution, etc. And I think in general, we understand that we cannot fully always have a resolution. We can't simply just increase resolution at every space and and even temporally solving, just because of the computational resource limits. But then the question is, obviously there are processes we cannot capture, we cannot fully resolve. Then we have parameterization for them. For example, KPP with their parameters that are tuned in that sense, for a certain resolution. But it does mean that actually, if we think the physics is somewhat captured in the parameterization, then we just need to have an understanding what kind of observation we need, or what kind of inversion method we can use to optimize for the parameters within the parameterization to see whether we can capture the process. So I think instead of fiddling around, maybe first I would use, let's say, a model. For example, if I were to cite the methodology Patrick mentioned, to use the adjoint. So if to use the adjoint, one would do, for example, look at a particular layer in the water column that we think should be where the maximum temperature, summer maximum temperature should be. And then we will now trace the sensitivity of how sensitive that temperature is to the various, parameter space in the model. And from there, you could actually learn something about which process that might actually be, if it was present at all to produce that water mass, and otherwise what process might be sort of detrimental or destroying. And that helps you to understand the parameters or the processes in the model that could be the result of why it was produced and destroyed or why it's missing altogether, as an example. So
Hello? Yeah. So I think it's kind of exciting because Effie, you've got this insanely high horizontal resolution, but 10 meters. And so we have an opportunity here. You've got that, and you don't have a summer Pacific Water TMAC. So that's information. That's great information. So now, easy for me to say, increase your vertical resolution. And if you get a summer TMAX, wow, we've learned a lot, haven't we? I mean, that would be just really interesting. But then there's the KPP point, so maybe, you know, we need to pay attention to that too. But anyway, I think, you know, there's an opportunity here that we can really learn something about what really matters for these things by doing it sort of step by step.
Wisla, do you want to add to that?
So actually,
We lost your audio. Yeah. I think.
my initial raising hand was on a different topic, but I can comment what I wrote in the chat. That we've tried increase horizontal resolution in the upper ocean by 15 vertical layers, and we have tried like 2.5 meter resolution in the upper ocean. At the same time, when we have a 2.4 kilometer horizontal resolution, and still excessive mixing is present, especially over longer time scales. So you can start with initial conditions which are reasonably well representing water masses, and after 10, 15 years, basically things got washed away. So I think it's pointing to some major structural problems in the model physics. KPP is a primary candidate, but I think that we're also probably having some issues with very primitive coupling of the atmosphere through sea ice to the ocean. And that's something that requires more effort and kind of like a process study and much more observations in terms of process observations. But what I wanted to say actually in terms of the, with reference to Patrick's presentation, which was great, I really appreciate it, is that I think that there's some ways maybe the modelers could cooperate better and more when, you know, like adjoint that you guys are using will point to ways to maybe tune some parameterizations in Earth system models that are poorly tuned or haven't been looked at that. At the same time, when people go to very high resolution, they can afford, you know, not even a 100-year simulation. They can afford a very short simulation. There's some issues related to what is the spin up from whatever your initial condition to adjust to your new high resolution dynamics in the ocean, which has not been addressed yet. But the point is that high resolution can tell you what probably the importance is, for example, of processes like eddies, like boundary currents, like the coastal currents in terms of contributing information to the ocean water masses and circulation, and then doing some type of data simulation and adjoint to optimize the parameter space. So I'm thinking about kind of like exchange of information between the one group of people going into very high resolution simulations, another group of people like what Anne and you are kind of like discussing in terms of optimizing with the physically based constraints and data assimilation. And then you're talking about the coarser resolution but fully coupled models taking advantage of those two results or experiences. I'm not sure if I'm clear, but that's the bottom line I'm thinking. Thank you.
This is Marianne Alberti from Princeton and GFDL, and I just wanted to add one other mixing parameterization to people's, I guess, attention to be considering for the Arctic or to be reconsidering for the Arctic. And so this is based on, we're doing the high resolution model development. That's led us to do a bunch of side experiments. And one, it's not a silver bullet, but it's certainly a parameterization that we found does make an important impact on the quality of the stratification in the Arctic, and that's the non-local internal wave driven dissipation. And so in our simulations, we use the Greg-Hennier style parameterization, and it's just physically not appropriate for the Arctic. And we find by turning it off and having background dissipation much lower, we start to improve our stratification significantly. And this is pushing us to just rethink how we parameterize the non-local dissipation from the internal tide globally. And I know there's a lot of different institutions leading efforts on this, but this is, I think, also we've found not a silver bullet, but important in how we realize the vertical stratification in the Arctic. So just also a thing to keep in mind.
So about this Pacific layer and the warm, summer Pacific water layer, the warm layer, and the too much molecular depths in the Canadian basin. Actually, I was waiting for the comment from Anne, but seemingly she's not want to mention her old paper that can actually solve this issue easily. I don't know why, but seemingly didn't mention this. I need to bring up this. So in Anne's paper, actually, she clearly showed that if you use this salt plume branch injection parameterization, this issue can be solved. And you will have reasonable molecular depth in the Canadian basin and well represent at Pacific water layer. But our practice that this scheme cannot be used for the Eurasian basin. And you need to set some cutoff. Otherwise, the molecular depth in the Eurasian basin will be too shallow, because it's a place where the shear-driven mixing is strong, and the salt should not be really put to the base of the mixed layer. But that, in this direction, it's tunable, and you can find a good compromisation and to really reduce molecular depth in the Canadian basin. Yeah, and maybe you want to comment more on that.
Yeah, maybe if I can try to reply. And as you can see, it was in response to trying to understand why a physical process was missing. At that time, our model as part of AOMIP, and we realized that because we don't capture the salt plume or the brine rejection correctly, or we don't capture it at the subgrid scale, and therefore we try to parameterize it. Then that's why I added a parameterization. And as you just alluded to, like any parameterization, it was built to try to capture a process, and therefore it has parameters within it. One is an example, for example, if you want to use to maintain a very strong halocline density gradient, salinity gradient, then there are certain schemes within that parameterization you would do. But then in the Eurasian, let's say, where you don't have, for example, as much, because it was meant to address, lead opening from landfast ice, and just off the shore you have the opening near the Chukchi Sea, for example, where you lose massive amount of heat, and therefore you actually form really dense water that can be detrimental if you don't mix it down correctly. But in the Eurasian basin, it might not be the case, and therefore actually it does require then to use the data in the upper ocean, for example, to try to understand whether this process is actually present, or how prominent it is, or how prominent leads are compared to the coastal regions, right? And therefore to use it appropriately. So that's another example of, for example, in that case, I was trying to determine whether the physics was there or not. And it turned out actually, without trying to maintain the halocline, or trying to produce the dense water that could supply the halocline, it was actually missing in many of the models, and that's why it was actually built try to capture, to parameterize that missing water mass or physics. And then it requires then the understanding maybe where it should be appropriately used, or if not, then how one has to adjust the parameters. So maybe similar also to the KPP scheme, you know, for the non-local source, whether it is appropriate in the Arctic, and therefore, if not, what kind of adjustment we need to do for a parameterization. And can I also address very quick, I think Mike's comment about increasing resolution, and then we learn something. That is true, actually, for even though we might not be able to afford it in, you know, long run, but for short run, like what Wislav said, you can actually run something to see whether you can resolve the process to capture the physics, because that's the idea of, if you want to increase the resolution to the point where you don't have to parameterize it, then if you do see that you can capture it, now you can use that in maybe like an OSSE sense, or even just, you know, to try to now revert back to the, when you don't resolve it and you had to revert to a parameterization, what kind of adjustment on the parameters you need to adjust there in order to match, for example, the physics you capture in the high res. So you can try to use it in that sense.
Okay, John, you want to make the final comment?
Final comment? Okay, quickly. Another set of physics to think about in these models is how is exchanges from the shelves in the deep ocean manifested. So Pacific summer water, Pacific winter water are coming off the shelves and entering the basin. Upwelling of Atlantic water onto the shelf in winter gets cooled, comes back down as denser water. That's a heat loss for the Atlantic layer. That's an important thing. We don't know a lot about the shelves, yet alone the shelf deep ocean exchange.
All right. Well, thank you, everybody. We're going to end the discussion there.